Anyway, as soon as I confirm here that we're live on YouTube, I got my phone going right here. Oh, there it is. All right, we're up. All right, so we can go ahead and get started. Let's see here. Got to turn off my phone, otherwise I'm going to get weird feedback problems. Okay, so today we're going to cover just the FIB side of this microscope, the Helios 650. And my plan is to just basically do two demonstrations. The first one will be a simple cross-section cut, which will make use of the gas injection system and the FIB to cut away material, and then we can see the buried microstructure under the surface. And the second application I'm going to show you will take longer. That'll be to do a full TEM sample and lift out. And if everything goes well, TEM samples on the Helios should take around 2 hours, start to finish. We'll see how it goes. So I have this system reserved for 4 hours, so we got till 5 p.m. That should be plenty of time, assuming I don't do something dumb like drop the sample or crash anything in the microscope. But we'll see how it goes. If you want to ask any questions, feel free. I would prefer you ask questions through the Zoom app for anyone that's watching on YouTube. It's easier, and the YouTube side of things, I have to look on there and look at the chat messages, so I probably will forget to do that. But feel free to interrupt me with questions as we go. I want to make sure you all learn everything that you need to know to use this system for your own applications. With that being said, let's go ahead and get started. I'm going to hide my webcam just because I don't really see why you have to be looking at the back of my head all day, but I'll turn it back on if I'm talking to you so you can see me. Okay, so you should be seeing the screen of the Helios right now, and I've already loaded samples into the system and pumped the chamber down. I've also already loaded a TEM half grid and a grid holder. So make sure when you come to use this, if you're going to do TEM applications, that is, make sure you bring your TEM half grids. Make sure you locate a half grid holder. We have some in the lab that you can use, but you don't want to be scrambling around trying to find that stuff right when it's time to get on the microscope. So make sure you have all that collected. And then I have my bulk sample in there as well. Now, if you, just as a comment here, if we look at my CCD chamber camera, my bulk sample is a piece of non-magnetic stainless steel. And it's a little bit on the tall side compared to the other samples. And this is kind of on the limit of what you can get away with on the Helios. I'm going to be really careful that I don't crash this thing into the lens as I'm moving around, but the safest thing whenever you have a sample like this is to do one sample at a time. So put the bulk sample in, do your FIB lift out, and then vent the chamber, take that thing out, and then you're only working with the half grid holder, which is much safer. And maybe if we have time, maybe I'll do that. I'll just vent and pull this thing out of there so it's not in the chamber. But this, I think, is safe. It's just you got to be more careful. The taller your samples are in relation to each other, the more dangerous it is. And you'll see as we get through here, as we start tilting and rotating the stage, there's potential for collisions. So the first thing we want to do is we want to go find our sample. And it's tempting to turn on the FIB and start playing around with the focused ion beam microscope, but one habit I really want to instill in everyone is that the gallium beam, the FIB ion beam, in this case it's a gallium beam, or on the other microscope it's a xenon beam, but that ion beam will cause significant damage to the surface of your sample, and we want to do everything we can to minimize that damage. And one of the easiest ways to prevent unnecessary problems is just leave the FIB off. Don't even click the beam on button until you're ready to use it. So we're gonna use just the SEM microscope, and we're gonna go find the sample. we're going to deposit a protective layer on the surface using the SEM, and then we'll turn on the FIB and we'll proceed from there with the FIB. But that way our region of interest will already have a protective layer on it, which should keep any of the gallium implantation and the gallium beam damage out of that surface. So let's go ahead and we'll click on quadrant 1. This is my SEM image, and I'm going to turn on my beam. Now, I've done some introductory trainings that are also on our YouTube channel that go over how to use the user interface, how to operate the SEM, how to move the stage around, things like that. So I'm not planning to cover any of that again today. But if you have questions, or if you see me do something that's not clear to you, again, ask questions and I'll be happy to answer those. So SEM is turned on. We'll start scanning. Let's go to a little bit faster scan speed, and I'll adjust my brightness and contrast. And I'm also going to check my starting conditions. I really like to use 2 kV on the Helios for my SEM. So I'm going to go to 2 kV and I'm going to go to 100 picoamps. This is personal preference. This is my kind of favorite condition on this microscope, but you can use whatever you want. It's not a real big concern of mine. All right, so we'll use our NavCam image to move around. So my NavCam, I already took the picture of the stage after I loaded the sample. So I've got my TEM half grid holder over here. This particular holder is the style that's made by Omniprobe. And I really like these holders. They're real short. They're real easy to use. You can put the samples in and out without any tools. They're real nice. They're a little bit on the pricey side, but we have 2 of them in MC squared, so you're welcome to come and borrow one of those anytime you need one, or people buy their own if you really want this one. There's other cheaper holders out there. Ted Pella makes a pretty nice one that's about $60, and it's a little bit on the blocky side, so it's kind of tall like my sample like this, but if you got 2 other tall samples in the chamber at the same time, that really doesn't matter. The rest of the samples here, this is the FEI alignment sample. I always put this in here when I'm doing trainings because there's a lot of useful stuff on here. If for some reason I have to go and take an aside moment to do something or talk about something, this is real nice to have in there, but plan is to not use this today. And then my sample is this kind of cube thing. It's just a piece of stainless steel. And as I mentioned, it's a non-magnetic type of stainless steel, so that's good. We can use the high-resolution objective lens on the SEM if I want to, but that doesn't really matter. Now, one thing you'll notice when I get over here, so I'm just going to double-click on it. We'll move over to that sample. This sample has not been polished, and the reason for that is I originally created this sample for doing some tests, experiments on the plasma FIB, and I didn't want a polished surface for that. But because it's not polished, it's just been ground with sandpaper through about 1,000 grit finish. You'll see that when we do a cross-section cut or when we make the TEM sample that there's a lot of damage in the surface. And I think it kind of looks neat. If this was like a real sample that I cared about, I would have polished it for sure. But just keep this in mind going forward, is that when you do a TEM lift out, your TEM sample is only going to come from the top 10 or 20 microns of your surface. So you generally need to have a pretty well polished surface. Otherwise your TEM lift out is coming out of a really damaged region of material. So I've done lift outs before on here. Let me see if I can find one of the previous lift out pits just to find something easy to focus on. Oh, here's one. So we always start out by first focusing on the surface of the sample and link our working distance to the z-axis of the stage. And then we're going to go to 4 millimeter working distance. So we'll go over here to Z and we're going to go to 4. 4 millimeters is our standard working distance on the Helios. It's also very close to the eucentric height of the stage. It's very important to locate the eucentric height when we're going to use the FIB. And the reason for that is we want to be able to tilt the sample back and forth without causing the features to move around a lot, which is a big annoyance. We also need to find the eucentric height because it guarantees that we're not going to crash the gas injectors or the Omniprobe needle into the surface of the sample when those insert. And you can't always trust the link between the focus and the z-axis, because maybe for new users especially, they may not be very good at it, and they might be off by a couple tenths of a millimeter. It also, the link between the working distance and the stage can change as you change accelerating voltage. And just to demonstrate that, let me show you what happens. If I go up to 20 kV accelerating voltage, and I'm going to focus on this hole right here, and we'll link our working distance. So we'll get in focus, I'll link, and we'll tell the stage to go to exactly 4. So at 20 kV, I think I'm exactly at 3.9998 working distance. Watch what happens if I drop down and say I'm imaging at 500 volts instead of 20 kV, which is totally reasonable. There's absolutely no reason you can't image at do this work at low voltage. In fact, if you have an insulating sample, you might want to be operating at low voltage. And so if I get down here and focus, adjust my astigmatism a little bit here at 5 kV and relink my working distance, oh look, we're not at 4.000, we're at 4.0837. So we're 83 microns different in our measurement of the sample height. Now that might not seem like a big deal to you, but keep in mind the gas injector needles only have 150 microns of clearance above the sample. So just being off, just by changing my accelerating voltage, I've already introduced an error that's like half of that distance. So again, you don't ever want to trust this link with the working distance, because it's not accurate enough. So let me go back to 2 kV, and we'll continue with finding the eucentric height. Now, the eucentric height of the stage is extremely repeatable. And what I mean by eucentric height is we're trying to locate the center of the tilt axis of the stage. And the way we do that is we're going to put an obvious reference feature right in the center of the SEM. So in this case, I'm just going to put this hole right in the center. And after I do that, I'm going to tilt the stage a little bit. I usually go to 10 degrees. And when the stage tilts, we're going to watch and see, does this feature appear to move up or down, or does it stay right in the center? And that's going to tell us whether our sample is too tall or too short relative to the eucentric height. So let's go ahead and do that. We're going to go to the tilt axis. I'm going to type in 10 degrees, and we'll hit enter. And we see as the stage tilts that hole moved in the up direction. So because the hole moved up, that means the stage is slightly too tall. And I want to use my stage Z slider control here in the navigation tab to bring that hole or whatever feature you're using. We want to bring that back to the center of the screen. So I'm just going to click the down arrow and hold on the down arrow for a few seconds, and we'll bring that point back. If you click in this kind of white area between the slider and the arrow, it'll move a little faster. So if you have to move a long way, you can click here. But the arrows are the smallest adjustment that you can do. So now I have the hole back in the center of the screen, which means we've now established the eucentric height between 0 degree stage tilt and 10 degree stage tilt. If our stage was mechanically perfect, like absolutely perfect alignment, then this would also be the eucentric height when we go to 52 degrees. What you'll generally find on these tools, though, is that there's a slight difference between the 10 degrees or 20 degrees or 52 degrees or whatever angle you go to. So it's going to be up to you to determine what two angles you want to use for setting eucentric. You should always use 0 degrees as one of them, and we'll use 52 as the other, because that's the angle of the FIB column, and that's going to be the most useful angle for us. So I'm going to continue up to 52 degrees on the stage tilt. And again, if the stage is really perfectly calibrated, then this will still be in the center when we get to 52, but most likely it'll drift off a couple microns. And you see that it did. So in this case, that hole is now slightly lower than the center of the screen. So it means I need to increase the height of the stage slightly. So I'm going to use my Z up slider, and I'll bring that hole back to the center. So now we've found the eucentric height between 0° stage tilt and 52° stage tilt, and we should now be able to go back and forth between those angles without seeing the features move around too much on the screen. And no matter what the working distance says, or no matter what the link over here on the z-axis says, you can always find the eucentric height within a couple micron precision. So it's very, very repeatable to do this. And this should always be your first step once you locate your region of interest, is find the eucentric height. And just to show you that we are right there, if I focus and link, if we look over here, the z-axis says we're at 4.08 millimeters. Again, it's not ever going to be right at 4.000 millimeters. So you go to 4 millimeters as a starting point, and then we find the eucentric height by tilting. Now, I'm going to just save my stage position here because I want to demonstrate something. This sample, I don't know if you can see in the camera here, it's not super flat on the top. And what will happen is, let's say I move over to a new spot. Like let's go over here somewhere. And let me find another feature. Here, we'll use this little scuff mark right here. Let's say this is now where I want to do my analysis. You're going to probably find that the eucentric height needs to be adjusted if you're in this region. So when I go to a new spot, it's just real quick. Just tilt to 10 degrees if you're not sure. Again, I had that feature in the center of the screen. And you see when I go to 10 degrees, that feature moved quite a bit, actually. Where'd it go? I think it was this thing, right? So bring it down. One thing is really helpful if you're going to set the eucentric height is pick an obvious feature. I thought I did, and I messed myself up here. So I'm going to go back to 0 tilt. And okay, yeah, it was that little dust particle. So we'll go to 10 degrees. And I kind of watch that thing drift down. All right, so we raise the stage up to put that feature in the center of the screen, continue to 52 degrees, do one more adjustment, and then we're all set. So this is not supposed to be a complicated procedure, but it is very important when you're using the FIB to always find the eucentric height of the stage. Right, so then we need to go up a couple more clicks, and now we should be good. I think that feature's right here. All right, so let's go back to where we were. I'm going to just double click on position 1, and that'll take us back to our previous position. And now I see that someone has turned on the Safe Stage Moves button. That's a good idea if you're worried about running into the lens, but if you have samples that are relatively flat, you probably don't need to have this option turned on. So that's in the stage drop-down menu. It costs you a little bit of time because the stage is going to drop and then move and then come back up each time. So I'm going to turn that off because I don't feel like I need it. But if I had a lot of weird, really tall stuff in the chamber, I would probably turn that on. Okay, so we found the eucentric height and we have set up our SEM. So the next thing to do is we're going to, let's move over a little bit because this area is going to be really damaged by the FIB. And let's just say this is going to be our area of interest. So let's update my stage position. Next procedure will be to deposit some kind of protective material on the surface of the sample. And we can do this using the SEM or the FIB, and that's going to be done with the gas injector controls. Gas injectors are controlled in the patterning tab. So we go to patterning tab, and then down here in the bottom are the available gas injectors on the tool. The Helios 650 has 3 chemistries on it. It has carbon, platinum, and insulator deposition, which is like a silicon oxide type material. You can use any one of these materials to make TEM or atom probe samples. So they all work as a structural glue or a welding material, and they all work as a capping material. So depending on what you're trying to do, you can use different things. I really like to use carbon as a first layer and platinum as a second layer. There's no reason you have to use one material for the whole process. I know lots of people that use platinum exclusively. It's kind of up to you what you want to do. Once we're in the area that we want, let's go ahead and insert the gas injector. Excuse me, insert the gas injector, and that's done by clicking on the little colored box that says in. So I'm going to insert the carbon, and I click on it, and it says, do you want to insert the GIS? And we'll say yes. And the gas injector comes in fairly quick, and if we lower the magnification on the SEM, you can see that this needle is fairly close to the sample. Now the carbon injector needle is probably several hundred microns away from the surface. The one that's really close is the platinum injector. So if I, just to show you this, I'll put the platinum in. The platinum needle, in ideal circumstances, the bottom of this needle, that edge that's kind of behind the needle, you can't see it, but that edge back there should only be 150 microns away from the sample surface. So again, make sure you're right at the eucentric height before you put in the gas injector. So again, let's go back. We're going to put the carbon needle in. And now what I want to do is to set up my beam conditions for doing deposition. SEM depositions are kind of on the slow side, so we want to do everything we can to make these go quicker. And the way to speed up SEM depositions is to use low accelerating voltage and high beam current. Low accelerating voltage to me means 5 kV or less. The lower voltage you go, the faster the deposition will grow. However, your resolution of your SEM starts to get really bad. And if you have bad SEM resolution, it'll translate into not a very well-defined pattern. So if you want to have a really nice square-edged, sharp deposition, you need to use higher voltages for your deposition. If you're just looking for speed, go with low voltages. So you can do it 500 volts, 1 kV, something like that. I really like 2 kV. That's been my voltage of choice for a while for doing SEM depositions. So I'm just going to leave the SEM at 2 kV. In terms of beam current, you want as much beam current as you think your sample can handle, with the caveat that you need to be able to see what's going on the surface. So a steel sample can take all the way up to 100 nanoamps of beam current. It's not going to hurt it. But if you're doing this work on a temperature-sensitive sample, maybe a polymer or something like that, you may want to avoid using these really high beam currents. Also, if your sample is an insulator, these high beam currents might cause some charge buildup, and that can cause your image to drift around, which means your pattern is going to look really terrible. For me, I'm going to use the 26 nanoamp beam current. I find this one works well, and it should produce reasonably good results. So as I change to that beam current, I want to double check my column alignment, make sure I'm getting all the electrons down the column that I can. So I'm going to open up direct adjustments. I'll go to crossover mode, and I'll check my source tilt spot. And then I also want to check my lens alignment and modulator. And this actually looks pretty good. There's a little bit of left-right shaking going on. That's probably good enough. Usually astigmatism is going to be the biggest concern with the large SEM beam currents. And as you can see here, as I go through focus, I've got a lot of astigmatism. So I'm going to go ahead and fix that. Let's see here. Focus, stigmator, stigmator. There we go. There's our image. All right, good enough. So now we're ready to actually draw a pattern on the screen and start depositing material. So again, I'm in the pattern control tab, and I'm going to select a rectangle pattern. There's a variety of patterns available in the patterning tab, but we're going to go with a rectangle pattern. So I'm going to select that, and I'll bring the mouse back to quadrant 1, and I'm just, here, let me make this full screen so you can see it easier. So I'm just going to click on the screen and drag with the mouse and then let go. And that draws a pattern on the screen. Now the pattern by itself just tells the microscope where to scan the beam. But in order to tell the software what we want to do underneath this area, we have to use the application file. And right now the application is set to none. I want to do a carbon deposition, so I'm going to open up this little drop-down menu, and I'm going to choose the carbon eDep surface application file. And that will tell the software to use the gas injector so that this deposits carbon. And it also tells the software what calculations to apply to measure or to predict how thick the deposition will be, which is this Z value here. Now we can resize the patterns by clicking on the corners of them, and we can drag these around, change their size. You can click on the little line segments in the middle as well. If you want to move the pattern around, you click on its border, but just don't click on the little nodes. So if I just click anywhere on the line, I can move and drag the pattern around. We can also rotate the pattern. If you move the mouse just outside the corners, the mouse will turn into a rotation icon, and then you can rotate the pattern however you see fit. You can also specify these coordinates exactly by going into the Advanced tab in the pattern screen, and we can put in an exact position. So if we want the pattern right in the center of the screen, we could set it to be 0x, 0y. And we can also specify the pattern rotation in degrees. The pattern size is on the basic tab. You have the X and the Y dimension. I'm going to do a 20 micron wide X. I think that's a pretty reasonable size for a cross section on this tool. It also happens to be the size that I want to do for my TEM lift out. So we're going to make the cross section first, and then we're going to use that same area for the TEM lift out just to save some time. For the Y dimension, this is going to vary based on what you're trying to do. For a TEM sample by itself, I'd probably go with 2 microns. If you're doing a cross section and you need to cut a little ways into the sample to maybe find a certain structure, you may want to do 3 to 5 microns for Y. It's just going to kind of depend on your application. But for what we're doing today, I'm going to go with 2 microns. Now the Z value is going to be the expected thickness of the carbon deposition. One of the weird or frustrating aspects of SEM depositions is that this value is almost always wrong. So even though it says 1 micron of deposition, I'll probably get some fraction of that value. I'll probably get a couple hundred nanometers at best. So don't think of this number as an absolute measurement, but it is useful for getting similar results across multiple depositions. So if I have 2 patterns, so say I have a pattern here and I draw another pattern here, if I set the Z value for 1 micron for both of them, then they'll both end up being the same thickness. And if I set the Z value to be 2 microns for pattern 2 and 1 micron for pattern 1, then this pattern will be twice as thick as pattern 1. But neither one is going to actually match this value. So you can work out a scaling factor if you care to. It's actually pretty consistent over the course of days or weeks on the microscope. So if you do need a very exact thickness, that'd be the way to do it. So make a test deposition, cut through it with the FIB, figure out how thick it was, and then scale the number to get the value you actually wanted in the first place. I'm going to go ahead and just use my own experience on this tool, and I know that if I set this to be 1.5 microns, that this will be a really reasonable carbon deposition for what I want to do. And once I have the pattern just the way I want it, to start the patterning, I'm going to go up here and I'm going to hit this play triangle button in the toolbar at the top that says start patterning. So I'm going to hit start, and when I do that, the gas injector needle will open up automatically, and now we are depositing carbon only in this pattern location. You can see if I change the brightness and contrast a little bit, it's only reflecting inside the pattern area. Now, this pattern is going to take about 5 minutes, and unfortunately, there's not a whole lot I can do to speed that up. So, if anyone has any questions about what we've seen so far, now would be a good time to ask them. Otherwise, we're just going to be sitting here for a couple minutes. Um,
Hey, Alan, I have a question.
Yeah.
Um, so let's say, so what I want to do eventually is I want to mill like arrays of these patterns
Yeah.
into my sample.
Mm-hmm.
Am I going to have to make these shapes one by one in this software, or does this thing take like CAD files and stuff that I can put in there?
So this software won't take a CAD file. It will accept formats called bitmap or stream file. So a bitmap image, right, is just like your normal bitmap. You can create an array of dots using some other software, and you can use that to control the patterning. But what kind of you just want arrays of like circles or dots or
Yeah,
points?
yeah, circles, pretty
Yeah.
much.
So let me show you. Once this is done, I'll take a moment to show you how to do that really easily. Because there's actually there's a tool in here that says build array.
Okay.
So what you would do is you would place a single shape, whether it's a rectangle or a circle, um, on the screen, and then you tell it to build array, and then you can create a repeating array of that shape, and it can be a fairly large number of points. I don't remember what it maxes out at, but you can at least do hundreds if you want to.
Okay, cool. Thanks.
So that's one option. The other option is, uh, let me go in here. If I open up the programs for FEI, there's another software on here called NanoBuilder, which this software, let me drag it over so you can actually see it. It's on the other monitor here. So the NanoBuilder software does read CAD files. So you can create a it takes GDS2 format CAD files, which is like a pretty standard one for doing lithography masks. So if you create your array using a GDS2 editor, that can be directly imported into this NanoBuilder software, and then this can control the FIB and make the cuts where you want it. So if it's a simple array, I'd probably do it out of the user interface, and if it's a more complicated array, I would do it out of NanoBuilder.
Okay, cool.
So I got a quick question.
Yeah.
So I just want to like use this to cut up polymer spheres and then look at the inner morphology of it.
Yeah.
So is that I would just kind of coat deposit the carbon on the whole polymer spheres and then use the FIB to cut it?
You don't have to coat the whole sphere. I would still go with like a bar, like I'm doing right now. It's just that in your case with the sphere, like say this is the sphere. If I just draw a circle on the screen, you would just put the bar kind of down the middle of the sphere or wherever you want to see the center line, and then we would use the FIB to cut away all this material on the lower half, and then that exposes the cross section, and you get a much better cut if you mill through a deposition layer than if you just cut a sphere in half.
Oh, okay.
Okay. So I would still follow this same general procedure. I would do an SEM deposition on the top, and then I would do a FIB deposition on top of that, and then cut it with the FIB.
Okay.
Okay.
Thanks.
So everything I'm going to show you here, just imagine that we're working on this on a sphere instead of on a flat surface, and it'll translate to your project.
Cool. So the purpose of deposition is kind of to protect the region where it got cut.
It serves several purposes. One is to protect the surface underneath the deposition from the FIB, but you also get a much better cross-section cut if you mill through the capping layer. And I can show you. We'll do the cross-section cut here through this where I'm setting it up, and I can do another little cross-section cut off to the side here where I don't have the deposition, and I'll show you kind of the difference of what happens there.
Okay, thanks.
Yeah. All right, so the deposition's finished. If I hide my pattern here and that's the measurements. I want to hide my pattern. And if I take a look with my SEM now, you can see that there's a black bar on the surface of the sample. That's where I've done the carbon deposition. And it's not going to be terribly thick. It's probably on the order of about 100 nanometers. And actually, you can see if I crank up my contrast, you can still see a little bit of texture of the surface through it. So it's still close to being transparent to an electron beam. But this should be enough to prevent the FIB ions from reaching the top surface of this sample when we do the FIB deposition. So let's turn our SEM back down to the lower beam current, because we don't need to be up at 26 nanoamps anymore. And let's get our focus back. So now what I want to do is I want to turn on the FIB, and I want to tilt the sample towards the FIB column, which is the column over here to the right on the CCD camera. That is going to be a 52-degree stage tilt. However, the software won't let me tilt the stage with this carbon gas injector needle inserted. If I look at my navigation tab, you'll see the tilt axis and the rotation axis are locked out. So what I need to do is go to my pattern control, remove the gas injector, and then the software will allow me to tilt. So now I'm going to go to 52 degrees. And then we'll use the FIB to add more material on top of this spot. All right, so we're tilted to 52, and if at the tilted condition, you can kind of see about the thickness here of how much carbon I put down, and you can see it's kind of on the order of, it's like maybe 100 nanometers. It's a little bump on the surface, but it's not a micron and a half by any means, which is what the software thought it would be. So now let's turn on the FIB. So we're going to click on quadrant 2, which is our ion beam signal. Remember that these quadrants can be changed. So if for some reason this is not the ion beam, you can always change it by clicking down here, change it to be the ion beam. And then we're going to go to the beam control tab, and we're going to just click beam on. Now this is assuming that the gallium field or the gallium ion emitter is actually on, and we can tell that because this bar is green. That means that we actually have gallium emission from the tip. And if you hover the mouse over it, it'll tell you some important things. One, it says the emission current is 2.1 microamps. It should be 2 nominally. So if for some reason the emission current was way off from 2, a value of 2, that could be a problem. Oop, what happened? Come on, pull up that status again. It also says another thing to look at is the operating time. Right now it says the operating time is 1,799 hours. The gallium source on the Helios has an expected lifetime of about 2,000 hours. And if you're going to start on a very critical experiment, you may want to pay attention to how much lifetime is left on the FIB, because once you get above 2,000 hours, that gallium source could run out of gallium at any time. We don't know when it'll happen. It could actually happen before 2,000 hours, but it gets more and more likely as that lifetime extends. So, and it's weird how life works, but it always seems to run out and shut off your FIB at the worst possible moment. So you'll have the Omniprobe needle in connected to your sample, and you're just about ready to do your lift out, and then the FIB will turn off, and that wrecks your sample. So again, just kind of pay attention to it. So if you come in to use the Helios and that says it's like 2,500 hours, just be careful that you may lose the FIB at any moment, and we don't really know when it'll go. So we should be okay. I mean, 1,800 hours is getting up there, but we probably have another week or so at least before our FIB source is going to go out. But it's a good thing to look at. Now, if this green bar is red, so that means that the FIB source is not turned on. And the way that you turn on the FIB source is the wake up button that's just above it. So wake up energizes the FIB source. The sleep button turns off the FIB source. I would prefer that users in our lab do not use the sleep button, unless you know for certain that this tool is not going to be used for about 24 hours. Every time you put the ion source to sleep and then wake it back up, it costs a pretty significant reduction in the lifetime of the source. So we've kind of made the decision here that we want about a 24-hour period of no use before we're going to put it to sleep. So if you know someone's coming in the next day or in 8 hours in the next morning, just hit the beam on button. Don't hit the sleep button. All right, so we hit beam on, and that will allow the accelerating voltage to turn on for the FIB. And now we can go ahead and start looking at our sample. Now we want to be careful that we don't cause a lot of excessive gallium damage to this surface. So a couple tricks that I like to do are, one, check your magnification on your FIB. Make sure it's similar to what your SEM is. So my SEM resolution right now is at 8000x. My FIB resolution is at 424x. So if I turn on my FIB right now and start scanning with the pause button, I'm going to cause a lot of gallium damage to a very large area of this sample. Now maybe that doesn't bother you, but if I'm worried about wrecking the surface, maybe I want to do another lift out on another day very close to this spot, I want to make sure I confine all my beam damage to just around this location. And the easiest way to do that would be just before I hit the pause button, just click on quad 2 and change the magnification with the big knob and turn that up so it matches the SEM magnification. Okay, the other thing that we can do to prevent excessive gallium damage in the sample is to minimize live scanning on the surface. I'm a big advocate of using the snapshot function. That allows you to get single scans over the surface, which really helps minimize the amount of damage you're going to cause to this area. Just as a reminder, the snapshots can be configured. So if we go to the scan menu and click on preferences, we can set the condition for the snapshot in the photo button. I like to use a snapshot of 100 nanoseconds for the FIB on this tool. I find that that's about the fastest scan speed that you can use and still see something. So let's go ahead and set that, and we'll see what happens. Let's see, some other considerations just before I start imaging with the FIB. If our sample is at the eucentric height and I have a feature right beneath the SEM, it should also be right beneath the FIB. However, it's a good idea to check the beam shift adjusters, because if the beam shifts are way off to one side or the other, that'll change where the beams intersect. So if I look on my SEM and I right click and say 0, that zeroes out my beam shift for my SEM. So let me double click and I'll put that carbon bar right in the center of the SEM. And now if I go to my FIB quad, you can see I've got a pretty significant amount of beam shift applied right now. So if I were to take an image, the FIB is probably going to look like down here somewhere. So I'm just going to right click and say 0 on the beam shifter. So now the SEM and the FIB should hopefully be real close to the same location. And let's go ahead and see what happens. So I'm going to come up here to the toolbar, and I'm going to click snapshot, and we got an image. Now, that image isn't fantastic. It looks like it's really on the bright side. But if you kind of look up here to the top, I think this is the carbon deposition right across the top here that I just did. So not a fantastic image, but it's good enough to see where the deposition is that I want to align. And actually, if you look on my SEM image, you can see the FIB mark right here from just that one scan. So again, it doesn't take a lot of gallium to affect the surface. And if you're working on a sample that has a thin film on it, even one FIB picture can wreck your sample, and then you got to start all over again. So I want my FIB to line up with my SEM image, so I'm going to use the beam shift to bring this carbon, the center of the carbon bar on the FIB to the center of the FIB image. The easiest way to do this is to hold the shift key down on the keyboard, and I'm going to left click the mouse up here in the center of the carbon, and I'm going to use the shift and the click to drag this to the center. So I hold shift, I'm going to click in the center of the carbon bar, And then I'm going to drag that spot to the center of the screen and let go. And you see that moved the beam shifter down and left a little bit. This has the advantage of allows you to do beam shift corrections without having to live scan on the surface. If you just click and drag this thing around or use the beam shifter XY knobs on the hand panel, you have to be live scanning to see what you're doing. But if you use this shift and mouse click technique, you can do it on a frozen image. So now let's take one more image just to see how good I got it. And it's pretty close. Maybe you can do that one more time. Shift and click, drag it, and we get it lined up. So just in like 2 or 3 FIB images, I've confirmed what I'm looking at, and I've got my beam shift fixed, so my SEM and FIB are perfectly coincident now. Now, one thing I'm going to change is the detector. Right now, the FIB is using the Everhard Thornley detector, just like the SEM. I much prefer on the Helios to use the ice detector for the FIB. So I'm going to go up here to my detectors, and I'm going to change it to ice detector. Another thing, I got ahead of myself here, and I didn't even look at it. I should have paid attention to my accelerating voltage and my beam current on my FIB. This is another way to reduce beam damage on the sample is don't image on the surface with a high beam current. And this is up at 0.43 nanoamps. I probably should have done this down at like maybe 40 picoamps or 24 picoamps because the lower beam current causes less sputtering damage for a given amount of time. So let me take another snapshot at that lower beam current. You can see the lower current is quite a bit noisier, but again, it causes less damage, and it's still enough of a signal to you can kind of pick out where the carbon is. Okay, so let's put the gas injector back in. So we'll go back to pattern control, and we're going to put the carbon injector in. And we're going to draw another shape on the screen. This time we're going to draw the shape on the FIB quad. So I'll go ahead and draw my rectangle on quad 2. And this time for the application file, I see a lot more choices here. Most of these are going to be cutting files for actually cutting into a sample, and I want to choose the one that says carbon depth. So carbon depth is the FIB carbon deposition application file, and if you remember on the SEM, the carbon edep file is for the SEM. And I'm just going to go ahead and delete that one so I don't get confused. And let's set the parameters to be the same dimensions, so 20 microns by 2 microns. The FIB depositions are calibrated correctly. So for the FIB, if I tell it I want 0.5 microns for Z, I will actually get within 10% of 0.5 microns. And that is much better calibrated than the SEM deposition. So FIB depositions, go ahead and use that value as is. SEM, you have to figure it out for your own purposes. Now, we need to choose the appropriate FIB beam current for doing this deposition. If your beam current is too low, then this deposition will take just way too long, on the order of hours. If our FIB current is too high, you won't actually deposit anything. You'll actually put a hole in your sample and you'll destroy your region of interest. So it's very important for FIB that you get the correct beam current. The way that we can estimate the beam current is based on calculating the area of this pattern in square microns and then multiplying it by a constant value. In this case, I would use 8 picoamps of beam current for every square micron of area. So just so we're clear, I'm going to run a calculator. Oh, can't type it. Right. So this pattern is 20 by 2, right? So 20 microns times 2 microns, and right, we're 40 square microns of area, and we're going to multiply that by 8, and that gives me a beam current of 320 picoamps. So 320 picoamps should be the ideal beam current to use for this pattern. Now, if I do another pattern that's smaller, I'd have to recalculate the optimum beam current. It'll probably be a smaller beam current. So just keep that in mind. You're not ever going to use the same beam currents if your pattern sizes are changing. So what we want to do is go up to our beam current list for the FIB, and we want to find the aperture that gives us the closest beam current to what I calculated. So 320 picoamps is also 0.32 nanoamps. So my optimum value is going to be somewhere between these two apertures, between the 0.23 nanoamp and the 0.43 nanoamp. I'm going to go on the conservative side. I'm going to go with the smaller beam current. So I'm going to choose 0.23 nanoamps. And this should be a suitable beam current to deposit carbon for this particular pattern size. Now each one of these beam current apertures may have a small shift in focus and a small shift in position and astigmatism. So after you change your beam current, we want to take a snapshot with the FIB and confirm that we're still looking at the same spot. Now I can't really see anything here because the brightness and contrast are so bad. So I'm going to turn down my brightness knob and then take another image, and you can see that looks a little better. And you can see here where the carbon deposition is located. Now, if I think my focus and astigmatism are bad, I can use the reduced area function, and that way I can keep the FIB from scanning on top of my carbon deposition. I want to try to preserve this area as much as I can to keep that pristine. But I don't care about scanning down here. I'm going to cut all this material away anyway. So let's check our focus with the FIB. So I have reduced area. I'm going to go ahead and hit the pause button. So now we're scanning down here, and I can try to adjust my focus and my astigmatism if I need to. All right, pretty good. And we'll pause, turn off the reduce area window. Let's do one more snapshot. And now we should be all set to do our deposition. If I need to position my pattern a little bit, instead of trying to move the screen around or move the stage, you can always just move the pattern. As long as the pattern fits in the screen, it will run anywhere on here. So there's no reason that you have to try to get the FIB alignment absolutely perfect. As long as you can see the area, this will be just fine. So I have my pattern right on top of the previous SEM deposition. I come up here and I hit play, and that will start the FIB deposition. This one is going to take 2 minutes and 58 seconds. And what we'll see, let me beam shift my SEM down a little bit, is that even with just a few seconds of FIB deposition, you'll see that the FIB deposits carbon considerably faster than the SEM, and it also deposits a much prettier shape. So much squarer edges, much nicer looking. We take another snapshot. So the snapshot tool is very nice because it pauses the FIB cut or the FIB deposition. It updates your SEM image, and then the pattern resumes on the FIB. So the snapshot's a really nice way to monitor what's going on with your deposition or your cuts.
Sorry, I was logging in. Oh, shit.
Sorry, I had a comment that the resolution for the Zoom screen share wasn't very good. I was checking it out on my phone while this deposition was running, and I forgot that the microphone would cause a feedback loop. Sorry about that. Okay, so deposition is finished, and if we take a look at what this did is we now have our 0.5 micron of carbon on the surface of the sample. Now, for just a simple cross-section, I would probably stop right here and I would do my cross-section cut, but I'm going to use this area for the TEM lift-out as well. And for me, what I like to do is add another deposition of platinum on top of this. So I like to do SEM carbon followed by FIB carbon followed by FIB platinum. And that works for me. You can feel free to use any recipe that you want, but that's what I'm going to do here. So to do platinum deposition on top of this, I need to remove the carbon injector, and I'm going to insert the platinum injector. And I can, if I want to, I could delete this pattern and redraw it, but I'm just going to save myself a few steps by changing the application file from carbon dep to platinum deposition, and that will tell the software to do platinum dep. Now, I'm going to do 1.5 microns of platinum, and the reason for that is I have prior experience doing steel lift outs like this, and I think I need that much material in order to have this be successful. Now, for platinum deposition, the optimum beam current is calculated using a slightly smaller value. It's used 6 picoamps per square micron, which for this, remember this is a 20 by 2 micron pattern, so 40 square microns times 6 gives me 240 picoamps, which happens to be really close to the beam current I'm currently using right now of 230. So I'm at a good beam current already, so I don't need to change my FIB beam current. But it's always good to check. You might have to. So let's do one quick snapshot. Just make sure nothing shifted on my FIB image. It actually did shift a little bit. I don't know if you can see here to the right of the pattern. My pattern doesn't quite line up anymore. Some of this shifting occurs when the gas injectors go in and out. So with the carbon injector in, this pattern lined up with the correct spot, but with the platinum injector in, it shifted the image over slightly. So always a very good idea, take a snapshot before you hit the start button. Make sure that nothing moved on you so you don't make a mistake. So I've got everything lined up. Let's do one more snapshot. Yeah, everything looks good, and I'll hit play. And that will start depositing platinum on here instead of carbon. And if I take a snapshot with the SEM, you'll see the carbon is a very dark color, and the platinum is much, much brighter. Okay, so this is going to be a good spot to take a break, I think. If you see here that we have 8 minutes and 40 seconds left for the platinum deposition, and I'm going to go step out of the room for a minute. So I will set a timer for about 8 minutes, and I will come back and we'll resume our cut at that time. All right, so I'll see you all in a few minutes. Okay, so our deposition's finished, and we can proceed with the next step. Okay, so let's take a look here. We should see we've got our platinum deposition we can see by FIB. And if we take a snapshot with the SEM, we have our 1.5 microns of platinum on top of the carbon. So now that we have all this this material, we have over 2 microns of material on the surface, we can be a little less cautious with the FIB scanning because we're going to cut away a lot of this material anyway, and the 2 microns of capping material will protect our region of interest really well. So what we want to do now is take out the gas injector, and we can delete our pattern, and we're going to drop our magnification a few notches on the system, and we're going to do the first step of a cross-section cut. So a cross-section cut is started typically by using a regular cross-section pattern. The regular cross-section patterns are drawn kind of like rectangles. So I select that pattern type, and I'm just going to click and draw a shape on the screen here. The difference between the rectangle and the regular cross-section is that a rectangle cut would cut a constant depth cut in this whole area, whereas the regular cross-section will cut a sloped trench. So there will be a deep side to the trench and a shallow side of the trench. The deep side is indicated by the thick yellow line at the top of the pattern, and the shallow side is the opposite, so down here on the bottom. So depending on which way you want your cuts to go, you can either rotate this pattern around like with the rotation controls, or you can leave the rotation alone and you can change the scanning direction to different directions. So for example, the default is bottom to top, but if we change it to be top to bottom, then now the deep side of the regular cross-section cut will be at the bottom of the pattern. So either way is equivalent. So again, you can rotate the pattern or you can change the scan direction. Let me set the rotation back to 0 and the scan direction to bottom to top. Now, the dimensions of this cross-section cut are going to depend on what you're trying to do. You may find that if you're looking for a thin film type application, you might only need to cut a relatively small area like this because we're usually going to try to cut about a 45-degree angle into the surface. So if we only need to cut a few microns deep, then we only need the Y dimension of the regular cross-section pit to be a few microns as well. For a TEM lift out in a material like this, I would aim for a depth of cut of around 20 microns or so, which means I need to have my Y dimension of this pattern also be around 20 microns. So let's go ahead and do 20 for Y. And by doing that, you see that my pattern has now fallen off the bottom of the quadrant. This will cause the microscope software to give you an error. So you have to have the pattern completely on the screen. So what we need to do is lower the magnification until the pattern completely fits, and then we can take a snapshot again to see the new result. Now the width of the cut, for just a cross-section purpose, I would just match the width of the platinum deposition I did. However, I know I'm going to do a TEM lift out in this site as well. So I want to have the pattern a couple microns wider on both sides of the platinum. I usually use 3 or 4 microns. That works pretty well, or more. Bigger is always easier. So in this case, here, let's go with 5 microns. So we'll do a 30 micron for X, 20 micron for Y. Now the Z value for regular cross sections is going to be the depth at the deep side of the regular cross-section cut. So if I set this to be 20 microns, then the side with the heavy yellow line should be 20 microns deep, and the opposite side should be come up to the surface of the sample. Now that depth only works if you're cutting the material that the application file is set to. So in this case, it's set to silicon. This is not silicon, it's stainless steel. Now, it's possible that there's another application file in here that might work, but I know we don't have any in here for cutting steel or even cutting iron. You see there's iron oxide, gallium arsenide, indium, or the IDEP is insulator depth, the indium phosphide, silicon, things like that. So what I need to do is I need to use either my intuition or my past experience to know what value to set this to get the appropriate depth of cut. And what I'm going to set it to is, let's try 30 microns. And I think that will produce a cross-section cut that is a reasonable depth. And if it doesn't, we can always cut it again. Now, with those settings, you see that the software predicts that this is going to take 23 hours and 7 minutes to cut. Now, when you're using the Helios, you're welcome to sit here for 23 hours, but I personally am not going to do that. The way to make this go faster is to increase the beam current on the FIB. So we're currently sitting in one of the middle beam currents. We can go all the way up to 65 nanoamp beam current, which will allow us to cut this much, much, much faster. If you're doing smaller cuts, you probably don't need to use these giant beam currents, but feel free to always try to maximize your efficiency on the tool. Do your cuts at the highest beam current that you're comfortable with. So just to show you how this works, I'm going to go all the way up to the 65 nanoamp beam. And even at 65 nanoamps, this cut's going to take 4 minutes and 50 seconds. So unfortunately, there's going to be more time here that we're just going to be sitting and waiting. Now, with the 65 nanoamp beam, be very, very careful about live scanning. This is enough beam current that even a few images will sputter away the platinum bar that I put down. So we definitely want to use snapshots. So I'm going to say take a snapshot, and we don't see anything. That's probably because the contrast is too low. So we're going to turn the contrast up. We'll take another snapshot, and now I can see where the platinum bar is. And what I want to do now is to make sure my beam is reasonably well focused. With the large beam currents, the easiest way to check this is doing what's called a spot burn. So what we're going to do is go to the scan menu, and we're going to put the beam in the spot mode. And I'm just going to put the beam over here to the side, somewhere where I don't really care. And I'm going to turn off the beam blanker, which is also in the scan dropdown. So I turn off the beam blanker. So now the beam is just sitting right here, drilling a hole in the sample. And then let's go back to full frame mode and take an image. And you can see here that we've left a hole in the sample. It'll probably show up better by SEM. And what we're looking for is, does that hole show any evidence that the FIB is out of focus? And does it show any evidence that we have astigmatism problems? Now that hole is pretty circular to me, which tells me our astigmatism is good. In my experience, the 65 nanoamp beam should make a hole somewhere around between 3 and 4 microns in diameter. So if I put a circle measurement on that, I can see that hole is about 5.5 microns, which tells me that this FIB is a little bit out of focus. So let's try to get this a little bit better. Again, we'll use the reduced area. I don't want to scan over top of anything that I care about. And let's see if we can get this looking a little bit better. So we'll start scanning, and we'll adjust our focus. Now, the 65 nanoamp beam is kind of tricky to focus. It's always going to produce a rather fuzzy image, and it helps to have one of these holes in the sample to see it. And what I want you to look for is, as I go back and forth in focus, you'll see on one side of focus, you get like a very sharp halo around the hole. And on the other side of focus, you get more of a diffuse halo around the hole. And where we want it for cutting purposes is we want those two kind of halos to kind of come together and minimize the effects of each other. And let me see if I can show this a little better. So again, here's one side of focus with that sharp halo around the hole. And as I go through focus, now you see on the other side, hopefully you can make this out. You see this sort of diffuse ring right here around it. So when those two halos kind of collapse into each other, right about there is the focal point. But you can see that that image still looks kind of fuzzy, and that's just the nature of the 65 nanoamp beam. Now, if I got this correct, let's do another spot burn right here, and it should be a smaller hole than this one was. So we go to scan, spot mode. Let's move the spot up here. Go to scan, turn off the beam blank, go back to scan, put it back to full frame mode, and let's take an image. And I didn't quite get it because that's even worse. So let's try again. You got to be pretty quick with the FIB at these beam currents because it sputters away the surface, and then you start getting weird effects. So let's try this again. Yeah, I think maybe like right here. So I'm going to use a keyboard shortcut, Control K to go to spot mode, Control B to activate the beam blanker, and then Control M. And all right, we're getting better here. So this one, if I measure it, yeah, we're kind of down in that 3 to 4 micron diameter range. So I think we're probably pretty well focused. If we're not sure, I can always do one more spot and let it just cut for a few seconds, so make a deeper hole here. So Control B, let it go for a couple seconds. Control M. And yeah, that looks pretty reasonable to me. If we look at it with the SEM, it's got a little bit of a fuzzy edge to it, but I'm not super concerned about that. I think it's going to be pretty suitable for what we want to do. Now, when we go to place our pattern, so let's go back to our FIB image here, and I'll unhide the pattern. When I place my pattern on the screen, when this cuts, the FIB will ride right down the line at the edge of this pattern. And this is how big in diameter the FIB beam is at 65 nanoamps. So this 3.5 micron diameter beam will go right down the center line of the yellow line. And if I have my pattern right up against the platinum, I hope you can see that I will cut away a good portion of my sample because that FIB diameter is so big. So always keep in mind what the size of your FIB is. So I want to back this, I want the beam to go, you know, right down the side of the platinum, so kind of like this, or maybe even give myself a little bit of extra leeway just in case. And that means I have to shift my pattern down somewhere like this. So when you're using these big beam currents, you need to keep your patterns pretty far away from your deposition. Otherwise, you're going to wreck your lift out before you even start. So let's go ahead and cut this, and we'll see what happens. So I'm going to take one more snapshot just to make sure everything looks good. I think that's pretty reasonable. Just a reminder of our settings. We're 30 micron X, 20 micron Y, 30 microns for Z, assuming it's silicon, and we'll see what depth of cut we get for this steel. So let's go up in here and we'll hit play. And now this will start cutting at the 65 nanoamps. And if we want to, we can take snapshots with the SEM and see what's going on. Just adjusting my contrast a little bit here, so that looks good. All right. All right, so we got about 4 minutes for this cut to finish, and we'll see what the result looks like.
I got a quick question.
Go ahead.
Yeah, so if I'm going to cut polymer, so
Right.
which setting should I choose for doing that?
So polymers are real. They can be very different. So it's gonna depend on exactly what type of material it is. So some of the harder polymers behave a lot like some metals. They cut very normally, and in that case, you use the highest beam current that you want, and everything just works. I've seen other materials, other polymer materials that when the FIB hits them, that tends to cause them to melt or to evaporate or form like bubbles and voids, and they're really tricky. And with those cases, you have to use smaller beam currents or even cut it with smaller accelerating voltage than 30 kV in order to keep the polymer from falling apart. So
Okay.
it's very, very, it's going to be a unique situation depending on what your material is.
Okay.
So hopefully
Thanks.
you have lots of material to do some test cuts, and you can just try
Yes.
cutting one and see what happens. And if it melts into a pile of goo, then you know you got to use more gentle cutting conditions.
Sure. Okay. Thanks.
Other options when you're cutting materials like that is you can use the cryo stage. So
Okay.
generally, our assumption is that the degradation of the polymer is thermally related. So if you cool the sample down with the cryo stage, you can then use the higher beam currents on the FIB to cut the material and without causing the damage. But adding the cryo stage into the procedure just increases the complexity of what you're doing. But that is another possibility to try.
Okay.
All right, so we're about halfway done with our cut. Let's see what our pit looks like. So it's going pretty good here.
So remember, because like I'm going to also use the SEM to look at the polymer.
Right.
So then, but without the quoting, then maybe is that you mentioned I have to use a lower um, voltage
Yeah.
to kind of image it.
Uh, right. But that's for the SEM, not the FIB. So the SEM and
Yeah.
FIB have different settings, right?
Yeah. Yeah. Sure.
Right.
But I mean, like for in the FIB, I can use the highest beam intensity or the beam current to cut it. It doesn't matter. But for the SEM, I would use lower one to look at the
Yeah.
image.
So the FIB generally doesn't have as many charge problems as the SEM does. So samples that would be difficult to image by SEM can oftentimes be imaged at 30 kV with the FIB, um,
Oh,
and it's not always a problem.
okay. Thanks.
So one of the big differences is how far the electrons go into a sample versus how far the ions go. So the ions stop within probably 30, 40 nanometers of the surface of the sample, and all that charge that's released by the FIB is all very near the surface of the sample, and it can generally uh, diffuse away very quickly. In the SEM, your electron beam can penetrate hundreds of nanometers into the surface, and it causes a lot more charge buildup problems because you're depositing all that current below the surface, and it can't get out quick enough. And at least that's my thoughts on it is that that's why the lower voltage SEM is usually better because the lower voltage confines the SEM electrons to that outer surface layer of the sample better, so the charge can leave the area quicker, so you have less problems.
Okay.
All
2 kilovolt we'll consider as a lower voltage.
For a lot of polymers, 2 kV is too high. I've done imaging on some polymers that you have to be in like the 100-volt kind of range in order
Okay.
to image them.
Okay. Thanks.
It varies a lot by the type of polymer and the structure and how it's prepared and things like that.
Sure.
Now, so this fib cut's done, and what I'm looking for is I want the bottom of this trench to disappear, so I can kind of see there's still some of this rough surface down here, which for me that tells me I haven't quite cut deep enough for what I want. So I'm going to go back and I'm going to increase my depth of cut a little bit more. Maybe not another 30 microns, but maybe I'm going to do another 10 micron cut depth. And I'm just going to run this again because I want all this material to be ejected from the pit. So let's go ahead and just run this again. It'll be another minute and a half or so. The reason I wanted the cut deeper is that, one, it gives you more field of view if you're doing a cross section, but this is going to be a TEM lift out as well. And I want to make sure I have enough height to pick up a decent size sample out of this pit. And how far down you can see is really what limits how tall of a sample we can extract. Okay, let's see what the depth of cut is now. It's a little better. In a perfect world, I would probably cut this again just to get rid of that last little bit, but I think this is deep enough for what I want to do. So let's move on with our prep. Now, when we go to do the TEM sample, I'm going to slide this pattern up to the top half of the screen, and I'm going to change the scan direction to be top to bottom. And then I would run this cut again, and I want to do the same cut I just did on the bottom half, also on the top half. But just so we can finish up the cross-section application, let's move on here. So the next step with the cross-section would be to clean up this face. So you can see here that the 65 nanoamp FIB beam has left this surface rather rough, and there's not a whole lot of microstructure to be seen right here. So what we want to do is we want to do another cut with a slightly smaller beam current to clean up this edge, and that should hopefully give us a nice, pretty cross-section view. I would recommend that whatever you use for your regular cross-section cut, drop your beam current by about 2 apertures, and then that should probably be okay for your cleanup cut. So let's drop down to the 21 nanoamp beam, and I'm going to have to check my focus and astigmatism again, so I'm going to do a snapshot. And I can see here, this is my image quality. It's not too bad, but let's double check, make sure my focus is good. Make sure my astigmatism is reasonable. And if I want to see how big the beam is, I can do my spot burn again. So Control K, Control B, Control M. And you can see the 21 nanoamp beam is quite a bit smaller than the 65 nanoamp aperture, which is going to give us a lot more control over where we cut. So now I'm going to use another type of pattern called a cleaning cross-section. And the cleaning cross-sections are, instead of cutting a sloped pit in the surface, these are used to remove the edge. So the cleaning cross-section is going to be drawn just like this. And we want to put the edge of the pattern right up next to the platinum this time. and we put the bottom edge of the pattern based on where I think the material is that needs to be removed. We're going to use, because we're using the silicon cleaning cross-section application file, it should have the same depth of cut as the regular cross-section did. So if I use the same Z value parameter, so I did 40 microns, right? I did a 30 micron depth, and then I did a second cut at 10 micron depth. This should result in the same depth of cut as the regular cross-section cut. And in order to see this edge a little better, I'm going to turn my contrast down. That flare on that edge can make it kind of hard to see where you have to put your pattern. So just kind of watch out for that. Let's just try maybe like this. That's going to take about a minute or so to do this cut. So always good idea, do one more snapshot, and then we'll hit play. And now the cleaning cross-section is running. The cleaning cross-section is going to cut line by line, starting from the bottom, and it's going to slowly advance up through the pattern area. So it acts like a meat slicer or something like that, it's just slowly shaving off this edge of the sample. And what we should see is that, oh, I got my contrast super high. We should see that the edge quality starts to improve as that beam starts to remove that material. Now, you're asking earlier why we need the platinum capping layer to cut through. This is, you can see here, this is the quality of a cross-section cut you're going to get if you don't cut through the deposition layer. And you'll see here that this is going to look kind of rough until the FIB gets up and starts actually cutting through the platinum, and this will smooth out dramatically, and it'll be much, much, much nicer. So we always want to cut through some kind of a deposition layer because your cross-section quality will be much better. The other thing that we're trying to avoid is you'll get some rounding of this edge if you don't cut through the deposition layer. So if you have any features up here in the top micron or two of a sample, they're going to look really bad unless you actually make your cut through the deposition layer first, and then it'll be much sharper, much straighter edge. So let's see how we're doing here. Yeah, getting there. We're almost up to the platinum. All right, now the 21 nanoamp beam is probably still a little bit on the high side for beam current. So if I really want this to look really nice, I'm going to do one more cut at one more reduced beam current, and that's going to be used to final clean up this site. So let's drop our beam current down again. I'm going to take it down 2 more steps to 2.5 nanoamps. And we'll go ahead and check our focus and astigmatism. Now this time, I'm just going to put a reduced area window down here on the bottom. These smaller beam currents, I don't really need to do the test spots to focus them. I can just use the features in the pit. So do focus, astigmatism, that looks pretty good. And I'm going to keep my pattern settings the same as they were. And this time we want to cut through just a little bit of that platinum. And let's shrink this down a little bit so it doesn't take quite as long. So something like this should be good. It's going to take another about 1:30, and we'll hit start. If I want to monitor my progress, I mentioned earlier I can take snapshots as I go, but I can do this automatically by turning on a feature called iSpy, which is located down here in the bottom of the pattern control. So if I turn on the iSpy and then unpause the SEM, the SEM will take images for me automatically after each one of these cleaning cross-section lines passes. And that's determined by this CCS line interval. It's set to 1 right now. So every time it does a cleaning cross-section line, I will get an updated image on my SEM. And I'm just going to change my magnification and beam shift a little bit here. And what I'm looking for is, once I think the quality of this face is appropriate, then I'll stop my pattern by hitting the square stop patterning button in the toolbar. And then I would be good to go ahead and do my imaging and whatever I need to do on this surface. And again, I expect a lot of these little vertical line artifacts, we call them curtains, these will go away once the FIB starts cutting through the deposition, through the platinum deposition. So we're not quite there yet. The FIB is still cutting just on the edge of the deposition. There is a limit to how far down you can cut with the FIB. As you can see here, that I'm getting a pretty smooth cut going down maybe 10 microns into the sample, and then the FIB starts to generate all these little curtain artifacts again. You can try to do a deeper depth of cut, or maybe try a smaller beam current, but to some extent you're limited to how far down you can cut with the beam. Now, I'm not super happy with that just yet, so what I'm going to do is I'm going to just run this one more time. I'm just going to nudge the pattern up just slightly and do one more cleanup cut there, just to try to get this a little bit prettier. And later on, when we're making a TEM sample, this strategy is what we'll use for thinning the sample. So we'll do these cleaning cross sections from both sides and work our way down to a electron transparent sample. So the procedure is very similar. It's just the sample will be lifted out from this pit first, and it'll be attached to a TEM grid. And I can actually tell I haven't even cross-sectioned all the way into the center line of the material because I can't even see the carbon depth that I did. Remember, I did SEM carbon followed by FIB carbon followed by FIB platinum. And if you look here on this cross-section of the deposition layer, I can't see all three of those materials. I just see the platinum. So I still am not quite all the way in to where I need to be for a real pretty sample. So let's just keep going here until we get to where we need. Now, what I'm doing is I'm being very conservative. I'm just taking off little bites of the side here until I get to where I want to go. This is a good approach if you're looking for a certain microstructure, like maybe you think there's a certain grain or something down in there, and you don't want to accidentally cut through it. So this is the way to go, is you start on the side of it, and you just slowly slice your way in, maybe 100 nanometers at a time until you find the structure you're looking for. But in this case, I'm just trying to get a nice looking surface. There we go. There. So that dark line that just showed up, that's the FIB carbon deposition. So now I know I've actually cut into the entire protected region of the sample. All right, so that's the basics of the cross section. Just if we want to see, kind of what this looks like, we can turn it to high resolution lens mode. and just kind of see what shows up now. So we always want to check our alignment if we're going to do the high resolution lens especially. So we can start off with source tilt. And then we can check our lens alignment. What I like to do is to move over to like one of these corners when I'm doing this. And that way you can try to image on something without, if you have some contamination issues on your microscope, you can avoid contaminating the face until you're actually ready to image. So we can fix our lens alignment by turning on the modulator. That's pretty good. And then let's fix our astigmatism. Now what we should see, if we're using a reasonable SEM condition and we have everything focused and aligned well, is we should see the grain structure in the platinum. So when the platinum deposits, it has these little like nanoparticles in it. And if you have your SEM resolution really tuned in well, you should be able to see that structure fairly easily. It shows up in TEM really well too, but you should see it by SEM. So now we've got everything dialed in, and if we go back over here to the center of the cross-section face, I'm going to change my, go to the tilt correction tab in navigation. I'm going to turn on dynamic focus, and I'm going to put it in cross-section mode. And then we can, let's turn up our contrast quite a bit. Maybe not that much. I'll double check my focus one more time. Yeah, good enough. And then let's do a nice slow scan. So we'll do something like 20 microseconds, and we'll see what this looks like. So we could probably still have a little bit of some curtain artifacts here. We could probably remove those by doing another cleanup cut at a little bit reduced beam current. There's also some other techniques called rocking polishing, where you can mill this on two different directions and try to get this to cancel out. Most of these curtains are coming from these voids that are in this top layer here. I mentioned this is a piece of stainless steel that I just polished with sandpaper through 1000 grit, and because I didn't polish it down to the real small diamonds, you know, like 1 micron or quarter micron diamond or anything like that, you can see there's this layer of deformed grain structure on the top here that is all, this is all from just grinding damage, basically. We want to do, so it's on the order of about 275 nanometers thick, maybe 300 nanometers thick. And this is what I was warning about. If you're doing TEM lift outs, make sure your sample surface is in good quality, because you know that's going to be part of a TEM sample that we make, which I guess if that's what you're studying, that would be interesting. But that's just the recrystallized region. And in terms of how far down the damage goes, you can see in a metallic sample, we're going to have quite a bit of evidence of dislocations and things like that extending pretty far down. I could see them better earlier. I think I did a nice slow scan in a better spot there. Oh, I picked up some astigmatism again, I think. like right here is a good spot where you can see the kind of the diffuse damage in the grain here coming from that top surface, and it just kind of slowly fades away as you go down. But even this contrast, like over here on the side where it's kind of cloudy, this is all mechanical damage from the top surface. So, you know, a good part of this TEM sample is affected by the top quality, even though it's going to be about a 10, 15 micron tall TEM lift out. So just watch out for that. All right, so that's the basics of a cross-section workflow. In terms of what we can do on this sample now is if we wanted to, I could use the EDS detector, and I could do an EDS chemical map on this sample. So the EDS detector is positioned to see this feature, so that's useful. You can't use the retractable backscatter detector for this. On the Helios, the retractable detector would crash into all this stuff. So you are limited to just the detectors that are up in the column. So the Everhart Thornley detector or the through lens detector. You can also, you know, as I demonstrated, you can do high resolution imaging on these features, things like that. So let's go back to our normal mode 1 lens, and we'll continue on with the TEM prep. So with a TEM sample, I wouldn't have done the cleanup cut. I would have just done the regular cross-section cut at 65 nanoamps, and I would have done that on both sides. So let's go back to that setup, and we'll continue on with that part of the procedure. So we want to go back to 65 nanoamps. Oh, before I forget, you asked a question about how to do the arrays. So it's very simple. You go into pattern and you do a rectangle, set up your conditions for what you want. So if you want to just do single spots that are the size of the beam, you would just set your dimensions of the rectangle to be extremely small. So you can set these to be like 1 nanometer by 1 nanometer or something like that. I think you can go even smaller than that. And we can just put that right in the center of the image. And then we, as long as that rectangle is selected, we can go in and we can say build array. And we can say maybe we want like 100 of these. We can do like 100 by 100. And we can do a pitch of, yeah, that's 10 nanometer by 10 nanometer pitch. Oh no, that's 1 nanometer. Let's do 10 nanometer pitch and say build. And then that's going to go ahead and raster all those patterns on the screen. Now, I probably should have done a less complicated pattern. This looks like it's going to take forever to build 10,000 of those shapes. So I'm going to hit cancel. And I'm going to say select all. And the select all button is really nice for this kind of thing. So that gets all those patterns, and I'll delete them, remove them all. If I do, let me do a little bit more reasonable pattern here. Let's do a 1 micron by 1 micron square. And then we'll put it right in the center, 0, 0. And then say build array, and we'll do 5 by 5. Let's make them 5 microns apart. Let's say build. And there's your array. So now if you want to move that around, you can say select all, and then you can move the array around to wherever you need it to be. And then when you hit play, those will all run in series, or you can change it to be parallel mode and run them all in parallel. When you build arrays like this, especially if you build one that's got like 1,000 elements to it, you don't want to sit and wait for it to rebuild every time. So what you would do is select all the patterns and go up here to File and say Export Pattern. And then if you just drop those somewhere, you just say like test array, put them somewhere in a file, and then the next time you come in to use the system, you just set up your FIB the way you want it, and you say File, Import Patterns, and that will bring in the array pattern just the way you had it before. And those arrays can be other shapes besides rectangles. They can be any of the polygon shapes. You could probably run arrays on cleaning cross sections and regular cross sections too, but I'm not sure why you'd want to do that. So anyway, that's how the arrays work in the user interface. And there's a similar function in that Nano Builder software that does that. All right, so we're back up to 65 nanoamps. We'll double check our focus, make sure this is still good. I always do a test spot at 65 nanoamps because again, it's kind of hard to focus that one. Yeah, see, I got it a little bit out of focus. Yeah, I'm still not happy with this. Got a little bit of astigmatism. Yeah, that's better. Nice round hole there. All right, so we're going to put a regular cross section on the top side. We're going to change the scan direction to be top to bottom this time. We'll set our dimensions to match before, so 30 by 20 by 40. And again, make sure your pattern is offset a little bit so that you don't take out your platinum deposition. If I want to be real picky about it, I can measure my last spot that I did there, place this. Yeah, should be good, just like that. Oh shoot, I just deleted my pattern. Unfortunately, there's no undo function in this software, so that was kind of a bummer. I got to go back and redraw it. So 30 by 20 by 40. The newer software on the Plasma FIB has a undo feature, which things like that are really aggravating. All right, I say that's pretty good, and I'm going to hit play. And now it starts scanning at the top side, and it comes down, and the deep end will be on the bottom here. So we're back on track for making our TEM lift out now. So we've got about 6 minutes for this to finish. So let's take another break and see you back here in about 6 minutes or so. Actually, I guess 5 minutes, 40 seconds now. All right, so the pattern's done. Let's take a look here. So we should have a roughly symmetrical cut now, that the back side of this lift out chunk should be about the same as this front side. So now what we want to do is we want to do the cleanup cut with the 21 nanoamps on the back. I'm not going to do the 2.5 nanoamp cleanup because that was just for this cross section to make that face look pretty. We really don't need to, you don't need to do that for the TEM lift out until this is on the TEM grid. So we'll go to our FIB and let's change our beam current to 21 nanoamps and get rid of our pattern. We need to check our focus and astigmatism each time, so we'll start off with a snapshot and we'll check focus, check astigmatism. That looks good. Take another snapshot. Too much zoomed in. Right, and now let's do our cleaning cross-section cut, which I actually don't need to remove very much here. It looks like I have my FIB go right up near the platinum. So remember, we have to change scan direction. We want to do a top to bottom cleaning cut. So something like this should be just fine, and we'll hit play. Okay, so now we have our thin little slice of material, and we want to do our undercut next, so we can pick this thing up and transfer it over to the waiting TEM grid. I'm going to keep the FIB at 21 nanoamps because I wanted this to go fairly quick, but we need to change the stage tilt so that we can actually get underneath this thing and cut it. We're going to go back to 0° tilt on the stage. And now I'm going to take a snapshot with my FIB, and I should be looking at the side view of the sample. And you can see here some really nice channeling contrast in that side. I'm going to use my beam shift, so shift, click, we'll drag this into the center. And let's pause our SEM scanning. Now to do the undercut, I'm going to use 3 rectangle patterns to cut along the left side, across the bottom, and on the right-hand side. So I'm going to select rectangle, and I'm going to draw pattern 1, just like this, pattern 2 across the bottom, and pattern 3 on the right-hand side. The 2 things that I see a lot of users do that will get you into trouble is they make these patterns really, really narrow because they think it'll save time. And it does save time in a way, but if your patterns are too skinny, it's really hard to see when you've actually cut through the material. And it also it leads to a lot of redeposition problems that can get the lift out stuck again. So I would caution you against making these patterns excessively small. Make sure they're at least, I would say, 2 or 3 microns wide. Otherwise, you can have problems. So here, let's go with, we'll make them 3 microns wide to see how that works out. The other problem that people will make when they're starting out here is they'll try to put the horizontal cut down at the bottom of the trench. So this is the bottom. The FIB image always appears like it's upside down when you're at 0 tilt. So this is the bottom side. You need to avoid doing this because if you cut right along this bottom edge right here, you're probably not going to get this chunk to come free and lift out. And the reason for that is I'm going to open up, let's see, paintbrush, so I can sketch on here. If we took a side view of what we've cut, we've got our original surface here, and we've got our regular cross-section trench like this, our sample in the middle, the other regular cross-section trench. Here's our surface, and we've got our capping layer on top here, the platinum, whatever. We're trying to use the FIB. The FIB's over here on an angle like this. We're trying to use that FIB beam to cut the bottom free here so that this chunk can be extracted. If you put your pattern right down here at the bottom of the trench, what happens is that your FIB cut will go like this. And usually what will happen is you'll leave behind a little bit of material right here that will keep that lift out from coming free. And sometimes it works and sometimes it doesn't. It really depends on how deep this cut is on the left side of my figure here. Because if this is cut deeper, then this will work out just fine. So what you want to guarantee that the lift out's going to work is you want your FIB cuts to exit kind of up here, you know, from like here to maybe right here. Which if you extend that back up parallel to the FIB, means that your FIB cut actually has to be placed here instead of down at the bottom of the pit. And if you divide this height up into thirds, I usually find that this is about 2/3 of the difference between this top and the bottom. So that's where we want to put our horizontal cut. You don't want to put it down in the bottom. Make sure it's up on the face a little bit. So if we go back to our image here, this is the top surface of the sample, right, where we can see the platinum deposition. And then here's the bottom of the pit. So if I divide that up into thirds, I want my horizontal line to be about here, about 2/3 of the way down. And again, make sure it's not super skinny. A couple microns tall is good. And something like this is what we want. Now, if you do a bunch of these lift outs and you don't want to draw these patterns all the time, you can do select all and you can export them as a file, and that way you can just import them every time, but that requires you to be using the same dimensions each time. Now, we want to run all three of these rectangle patterns at the same time, and the default setting will run this in serial mode. So what we do is go up here, and this button in the top right of patterning is going to change it to parallel mode, and that'll run all three patterns at the same time. The last setting to look at would be the depth of cut. So I'm going to select all three patterns. And I don't really want a very specific depth here. I just want to cut until I can see light all the way around here. So I'm just going to set this to be some big value, like 10 microns, because I'm going to stop it earlier no matter what happens. Let's do one more snapshot and make sure everything looks good. Yeah, see it drifted a little bit. So let's select all the patterns. We'll slide this over slightly, and we're going to hit play. Now, at 21 nanoamps, this cut shouldn't take too long, maybe a minute or two. And what we're looking for is evidence that the beam is punching through into the backside, which should show up as like black holes, generally in the corners first. A sample like this, it has a lot of grain structure, and it can be a little bit hard to interpret, but we're looking for just kind of like a uniform black color to go all the way across in these pattern areas. So I think this structure that's changing right here, I think that's a hole. This is probably a hole too, now that it's kind of uniform black going all the way across, but I'm just going to let it cut for a few more seconds just to make sure. All right, we're probably good. So I'm going to hit stop on the pattern, and we can take a look with our SEM and see what we've got here. And we can see on the SEM image that that pattern has now been cut into this back wall here. So this sort of upside down J cut, and that's a good indication that we're cut all the way through, right? I can't see any gaps in that pattern, so we should be okay. Now, when the FIB hits this back wall, it does have a tendency to sputter material onto this back face of the lift out. And if that's really excessive, these little corners can actually grow out and make contact with this face. And that can get your lift out stuck. So what I like to do is to do a quick cleanup cut. We'll go back to 52-degree stage tilt. And I'm just going to use a rectangle pattern to just kind of skim off that debris from this front face of the lift out. And that just takes a few seconds. So we're back at 52 degrees. Let me check my focus with my FIB. I probably should be using the reduced area window here, but I'm being quick about it. All right, so we want to just place a rectangle pattern just kind of along the bottom edge of the sample, and then we're just going to run this for a few seconds, and you'll see that a lot of that debris will go away really quickly. All right, that should be good. That's all it takes. So now if I take a look, this face will be nice and clean again, and all that stuff on the corners has been removed. All right, so now we're ready to actually do the lift out. So to set up for the lift out, we're going to go to 0-degree stage tilt. Now you can do the lift out at positive stage tilt if you're trying to set up other types of samples, say like a plan view TEM lift out or inverted TEM samples. You can do those lift outs with the stage tilted, but conventional TEM sample is done with the stage at 0 degrees. I'm going to make sure that I don't have any beam shift on either my SEM or my FIB, so zero out your beam shifts. And I'm going to turn my FIB beam current down to 24 picoamps. The reason I'm doing that is, one, the small beam current is nice for imaging because it won't sputter away the side of the sample very quickly. And two, it's the right beam current when we go to weld the Omniprobe needle to the side of the sample. So by being at 24 picoamps, it saves me from having to change my, my FIB current again later. So let me double check my image on my FIB. Now, without any beam shift on the FIB, and you can see that the sample is not in the center of the FIB image anymore. I've been at the eucentric height this whole time, but once you get to the Omniprobe lift-out step, you want to position the sample at the coincident point between the FIB and the SEM. So the way we do that is make sure your beam shifts are zeroed out, and then just put the sample right underneath the center of the SEM, and then also look with the FIB, and then we're just going to make a small adjustment to the stage height so that that sample is right underneath the FIB as well. The reason we're doing this is because the Omniprobe position is calibrated based on the coincidence between the FIB and the SEM beams. It's not calibrated based on the eucentric height. So if you want to use the coordinate system that the Omniprobe has, it's better to be at this position than at the eucentric height. Now, you can see those two positions were only about 10 microns apart, but if you want to, again, if you want to really trust the Omniprobe coordinates, this is the location that they're based off of, not the eucentric height of the stage. Now, the Omniprobe controls are run on the support computer, which, if you're in the microscope room, it's just to the left of the microscope. I'm going to show the desktop of the support computer, and I've got the window cropped to only show the AutoProbe software. And I think this will be an okay spot to leave it. Just kind of right here. Now, the AutoProbe software has a couple kind of areas for moving the Omniprobe around. So you've got an X and a Y control. Excuse me. and those are moved by just hitting the arrow. So up, down, left, right, and then you've got the diagonals. You also have a Z control. So if you click on the Z button, you can move the probe up and you can move the probe down. The speeds are controlled by selecting these different speeds in microns per second. So you can make the probe move faster or slower as you want to. The Omniprobe has 3 reference positions over here: eucentric, eucentric high, and park. The eucentric point is when the Omniprobe is right at the coincident point between the SEM and the FIB beam. So right now, where our sample is located, that's what the Omniprobe software calls the eucentric. Eucentric high is 300 microns directly above this position. So the probe would be in the center of the SEM screen, but it will be 300 microns above the sample. The park position retracts the probe back 1 millimeter parallel to the probe shaft. So if you've never seen the Helios, let me turn on the webcam for a second. Right, so here's me. So if we turn around there and look, so the Omniprobe is this thing right here on the front of the microscope, and you see it's on an angle. It's actually on a 50-degree angle to the port. So the park position retracts the needle parallel to that direction, 1 millimeter. Now, when we want to use the Omniprobe, we have to actually insert that device into the chamber. The controls that I'm showing you, the autoprobe controls, these move the needle around relative to the Omniprobe body itself, but that whole assembly has to be inserted into the chamber in order to use it. And that control, the insertion control, is done on the FEI software, not in the autoprobe software. So just to show you what's going to happen here, if I don't know if I can get this to balance. Sorry about the dizziness. There, I'm kind of looking straight up at the bottom of the Omniprobe here. So if I go into the software, I'm going to go to the patterning control tab, and the Omniprobe controls, let me move this up here. The Omniprobe controls are right here above the gas injector control where it says Insert Omniprobe. So when I click on Insert Omniprobe, this whole assembly is going to insert. Now, before you put the Omniprobe in, you want to make sure it's at the park position. If it's not, if someone left it at the eucentric point and you insert the Omniprobe, it could very well crash into your sample and wreck your lift out. So what we want to do is go over to the autoprobe controls, and we're going to click on the park position, and we're just going to click Go To. And that will make sure that the Omniprobe is at park. Now, it may have been at park anyway, but we just want to make sure that we don't damage our sample. All right, so the Omniprobe stopped moving, and now we're going to go ahead and insert it. So we are going to click on Insert Omniprobe, and the software pops up a message and says, do you want to insert the Omniprobe needle? And we'll go ahead and hit yes, and that will cause the whole Omniprobe assembly to insert. Okay, so hopefully, now that the probe's in, we don't need to look at this webcam image anymore. Let me turn this off. Webcam. Now, if you're really up close to the monitor, you can see the Omniprobe needle in the background on the CCD camera, but it doesn't show up really well. It's pretty small. I don't know if you can kind of see it right here. It's kind of fuzzy. It's hard to see. However, you should easily be able to see it with the SEM. So if I take my SEM image and I lower my magnification all the way out, you can see the Omniprobe needle over here on the left side of the screen. So this is the park position for the probe. So the first step we're going to do is we're going to move it to eucentric high. So I'm going to go to my Omniprobe software, the autoprobe software. I'm going to click eucentric high, and then I'll click Go To. And that'll cause the probe to move to that eucentric high point, which again is 300 microns above the sample surface. All right, so now we're at eucentric high. The next step is to lower the probe down to the surface of the sample. Now, if your material is not very sensitive to the ion beam, you can just simply lower your FIB magnification and you'll be able to see the Omniprobe, and you can watch it as you lower it down and make sure you don't crash into the sample. However, if your sample is beam sensitive, you need to bring this probe down without dropping your FIB magnification. And the way you do that is by looking at these reference coordinates on the Omniprobe software. So right now, for the Z control, it shows that my coordinate is negative 442 microns. Now, these are just relative numbers. That number will change as people change the probe out and things like that. But for now, it says negative 442. So because I know the probe is 300 microns above the sample, if I take away 300 microns from this number, that's the coordinate where the probe should hit the surface. So if I go down to negative 742 microns, that is where I collide with the sample. So what I can do is just carefully maybe go like 20 or 30 microns a second, and I'm just going to go ahead and click Z, and I'm going to go down, and maybe I'll start looking at when I get to like the maybe negative 650, maybe minus 700 range. I'll take a look with the FIB and I'll start watching for the probe. So let's just go ahead and let's bring it down to minus 700. So 600. Again, the eucentric point is that negative 742. So we're not quite there yet. All right, so we're at minus 700. So we should be 40 microns above the surface. I'm going to reposition my needle. I'm just going to put the point in the center of the SEM. So I'm going to click the XY control. Let's go down to like 5 microns a second, and I'll go to the left with the X. All right, and now let's go over to the FIB, and we'll start scanning with the FIB, and let's see if we can see the probe. We can't see the probe yet. Here, let me use my beam shifter to get centered. So I'm just going to carefully keep lowering the probe down. So I click Z. Let's stay at this 5 microns a second, and we just keep going Z down. And eventually we'll see the probe come into our field of view. There it is. So here's the end of the probe. We don't want to necessarily touch the sample just yet because we don't have our gas injector inserted. When you insert the gas injector, it'll cause everything to shake a little bit. So if the Omniprobe needle is touching the sample, that vibration maybe could break off this connecting tab, and that could potentially cause you to lose your sample. So once you get the probe close but not touching, then go ahead and insert the gas injector that you're going to use. I'm going to use the carbon injector for this one, so I'm just going to click carbon and then say yes. And you see when the needle comes in, it causes that, when the gas injector needle comes in, it causes the probe to shake a little bit. So now what we want to do is position that Omniprobe needle right next to the side of the sample. You always want to start with your SEM image because if you start with your FIB image, it's very confusing to know where the probe is because the FIB is looking at this from a side view. So you can only determine the height of the Omniprobe if you know the probe is directly above a feature. But from this FIB image, like if I didn't know if the probe was above the sample or maybe the probe was above this edge of the lift out, those are two really different heights. So I need to start with the SEM image and make sure I know where that probe is. So I'm going to use the SEM image, position that probe right over that gap on the left side of the sample and get it aligned with the center line of the lift out. And then I go to my FIB, and now I know I'm this high above the lift out. So I go to my Z control, and we'll go Z down. Just so the FIB, I want to bring the probe to the right hand, to the right just a little bit, just so it's close to the sample. I'm going to use the 0.5 micron per second speed, nice and slow. And we're just going to use XY and go right. Now, if you touch the sample, you usually see a contrast change in the image, or you'll see this sample start to bend a little bit. So if I actually make contact with it, you see that the image shifted just a little bit. but again, I don't really want to touch it. I want to just be close, just like it is right now. Just that's about 400 nanometers away. And we're going to fill in that space between the probe and the sample with the carbon deposition. Now you can also do this with platinum. So let's pause our scan, and we're going to click rectangle pattern. And let's draw a rectangle right in between the probe and the side of the sample, just like this. We're going to change it to be carbon depth. And the thickness isn't really critical. If you really want a number, I would say maybe 0.3 or 0.4 microns is fine. I'm just going to run it until I see that gap fill in with carbon. So then we go and hit start pattern. And just so hopefully you can see this a little bit better, let's make it full screen. And of course, I've got the Omniprobe screen over top of that. So we're watching for that gap to close up between the side of the sample and the Omniprobe. And you'll usually see that contrast change occur when the two come together. Or at least sometimes you do, especially with the platinum, you'll see it. One important consideration is that when you have the Omniprobe in, be really careful not to double click the mouse on the screen because you don't want to accidentally move the stage. That can bend the Omniprobe needle or cause your sample to get damaged. All right, so I think this is good. The gap is closed up, and I think the probe is connected to the side of the sample. So I'm going to stop the patterning. And now what we want to do is cut off the connecting tab on the right side. So I'm just going to use my beam shift. So either the beam shift knob or the shift and mouse click, whatever. But I'm going to beam shift over to the right-hand side. And now I want to use my FIB to cut through this material right here. You're going to need more beam current for this. I would say either the 0.79 nanoamp or maybe the 2.5 nanoamp beam, depending on what material you're cutting and how thick it is. I'm going to go with the 2.5 nanoamp just because it'll cut fast. So once your beam changes, take a snapshot. And this is kind of out of focus, but it's not too bad. And I'm more worried about time, so I'm just gonna cut it. If your sample is not stable, it'll be moving and drifting. And what'll happen is you'll break off the Omniprobe. So you want to be fairly efficient about doing this. So if it's slightly out of focus, don't worry about it. Just cut it and everything will be fine. So we put our rectangle pattern over the connecting bridge. I set the Z value to be a couple microns just so I have enough time to cut through there. Do a snapshot, make sure everything looks good, and then we hit play. And we're going to go ahead and cut that. And you can see in the real-time image under the pattern that this will cut fairly quick at 2.5 nanoamps. So that's all done. We'll stop the pattern. And then let's go back down to our smaller beam current, back to the 24 picoamps. And I can delete this pattern. A good way to check if the sample is actually free from the surface is to just lightly tap on the side of the microscope frame. And what you'll see is if the sample and the Omniprobe shake together, then you know that it's no longer connected to the bottom of the pit, and you should be okay to raise the sample and the probe up. So if the sample doesn't shake like that, then you're probably still connected somewhere, and you should keep trying to cut it free and get it loose. Just to demonstrate what I'm doing there, let me turn the webcam on for a second. So here's the microscope table. So this corner right here is usually what I tap. So I just take my hand and just kind of gently tap it like this, and that'll cause enough vibration to get the probe to shake. What you don't want to do is you don't want to go up here and like punch the side of the chamber, because if you cause enough vibration, you'll break off the Omniprobe on the side of the sample pit. So just kind of right here on the front is a good spot. Okay, so let's go ahead and raise the sample out of the pit. I like to watch this with the FIB image just to make sure I don't run into anything. So as we raise the lift out, we want to make sure we don't snag on this edge here or snag on the left side. So just go nice and slow. We're going to use the Z control, Z up, and click on the up button, and we'll just slowly raise that sample out of the pit. Once you're clear of the surface, you can go a little faster. Just keep bringing the sample up. And once you're away from the pit, then we're going to move the sample to the park position. And that's done just by clicking on park in the Omniprobe software and then say go to. And that'll bring the sample back to park. Because the park position is on an angle, make sure you don't go directly to park when the sample is down here in the pit, because it'll catch on this left side and it'll rip your sample off the Omniprobe. So you always have to manually go up first, and then you can go to park. All right, so now the sample is back at park, way back here. We can remove the gas injector, and we're going to remove the Omniprobe from the insert position, and then we're going to go over to our TEM grid. I strongly recommend removing the gas injector first. On some systems, not necessarily this Helios, but on some FIBs that they may have some mechanical issues. If you remove the Omniprobe first, sometimes the Omniprobe needle kind of swings around a little bit when it's retracting, and it can run into the gas injectors. In this case, you can see there's like a mile between the two, but with some of the other injectors, like the platinum injector, that it's much closer to the Omniprobe needle. So it's always safer to take the gas injector out first and then retract the Omniprobe second. That's just one of those things I've learned over the years. So we take out the gas injector, then we pull the Omniprobe. And now what we want to do is we want to use our NavCam image to go over to our TEM grid. So on the NavCam, I'm just going to click on the TEM grid holder, and we'll head over, find that sample. All right, so here's the TEM grid holder. I'm looking for the half grid. It's around here somewhere. So there's one of the empty spots, so it's on the other side. There it is. All right, so here's the TEM grid. This one actually has a sample on it already that I made with the plasma FIB the other day, but we're going to just keep using the grid for our purposes. So when you get to the new sample, make sure that you zoom in on it, focus, and update your link to the working distance. And then we're going to move this to be at 4 millimeters. Now, we want to change the rotation of the stage. We want this half grid to be parallel to the screen. So I'm going to go to Stage dropdown. I'm going to use a feature called XT Align feature. That allows me to draw a line on the screen, and the stage will then rotate to make this feature straight. And let me move the auto probe screen out of the way. Okay. Now, the TEM half grids, especially these ones made out of copper, they have kind of this characteristic shape to them. It's like a mushroom shape. I find it's easier to attach samples if the curvy side is up. So in that case, I want to rotate this 180 degrees, because again, I want this kind of curvy side here to be on the top. So to do that, we just come over, we're going to change our stage coordinates to relative, and we're going to do a relative 180 degree rotation. And hopefully you were watching the CCD camera there, and you can appreciate how close that tall sample just came to the lens. This is why you got to be really careful when you have differing heights in there, is that if it's anything much taller than that, you can risk hitting the lens when the stage rotates. So, all right, let's align. I'm going to do one more alignment on this grid just to make sure it's nice and straight. That looks pretty good. and then we can pick which finger we want to attach to. I'm going to go ahead and put it on this, the left side of this finger, but where you put it is up to you. Now, if I want to set the height of this real exact, I can try to tilt this and find the eucentric height. And that's a totally reasonable way to do this. But it's actually just as fast to just look with the FIB. Just like we set the sample before to the FIB coincident point we put a feature underneath the SEM, and then I raised and lowered the stage so the lift out was right under the FIB. I can do the same exact thing with the Omniprobe grid. So if I start imaging with the FIB, I should see the grid finger here, and wherever I'm going to attach that sample, I want that to be in the center of the FIB image. So I'm just going to go ahead and raise the stage up a few 100 microns so that wherever my sample wants to be attached is right in the center line of the FIB. And you should do this without any beam shift. Actually, I have a lot of beam shift on my SEM. So let's go back and double check. So got rid of my beam shifts. I can put the corner of the grid finger right under the SEM. And then if I look with the FIB, wherever I'm going to attach the sample, I want that to be right in the center. So this looks good. Let's go ahead and reinsert the Omniprobe, and we'll reinsert the gas injector, and we're going to bring that sample down next to the grid, and we're going to weld it to the side of the grid finger. So let's do the Omniprobe first. Remember, the Omniprobe is still at the park position, so I can say insert, and that should be safe. Right, so here's the probe over here on the side. And let's go ahead and move it to the eucentric high position. All right, so that should be 300 microns above the image of the FIB. Now, normally I would just lower the FIB magnification and you can see the lift out right now, but because I have a thin sample already on this grid over here to the right, I don't want to wreck that sample with the FIB. So I'm going to just use my coordinates on the Omniprobe again. I'm going to start off by first moving the sample over to the left, because if I bring the sample down, straight down, it's going to run into the top of this finger. So let's use the XY coordinate, and we'll just move that lift out way over here to the left-hand side. And then I can bring it down in Z and avoid crashing into the grid finger. So here's the lift out right here. You can see I'm well off to the left, and I'm not going to hit anything. So just keep bringing that down until we get it to the location we want. In this case, I want it to be in the center line of the FIB. Let's go ahead and bring in our gas injector now. So we'll put the carbon injector back in. And now we want to be a little more careful and bring that sample right up and touch the side of the copper grid. Okay, so we'll start with the SEM image. We'll bring that sample, bring the lift out a little bit closer. Something like that looks good. We'll double check the alignment in the Y direction. We just want the lift out to be kind of in the center between the two edges of the half grid. That way, if this falls on the counter or something when you're loading in the TEM, this isn't going to get knocked off by hitting the counter. So it gives it kind of some protection. So where it is right now looks pretty reasonable. And so now on the FIB image, we just want to adjust the height so it's centered in the FIB, and then we're going to just bring it to the right until it just barely touches this surface of copper. Now, you can usually see that it's getting close because there'll be a shadow that forms right here on the side of the half grid. So as I slowly bring that over, you can kind of see the shadow forming right here. So the shadow is going to tell me like where it's going to actually contact the grid. So just keep going until it just barely touches right there. And you can see the image is kind of shaking a little bit when it makes contact. You can push it in just a little bit more if you want to, but as you keep going, eventually you're going to start to bend this thing and it's going to deflect, and that could lead to problems. All right, so let's go ahead and connect this thing to the grid. We're going to do a carbon deposition because I have the carbon injector in using a rectangle pattern where you put the rectangle pattern kind of over this gap between the grid and the sample. We'll change that to be carbon dep. And just like before with the depositions, we need to make sure our beam current is correct. So you can calculate this out, right? 7 microns times 1.7 times 8. But I know from experience, it's going to either be the 0.23 or the 80 picoamp. I think in this case, I'm going to go with the 80 picoamps. And this should work out pretty good. Check my focus, check my astigmatism. And then we'll go ahead and run this deposition. 0.5 microns is a pretty good value for this. That's usually enough carbon or platinum to get the sample to be attached to the grid. And then we can always add more carbon later if we think it needs more. So once this deposition is finished, I'm going to beam shift to the left over to where the Omniprobe is attached to the lift out and turn up my beam current a little bit higher beam current, and then we'll cut off the Omniprobe from the side of the lift out. All right, so should be attached. We'll beam shift over this way, and then we want to cut through this weld right here. So let's turn up our beam current a little bit, maybe like 0.43 nanoamps. I need to change my pattern instead of a deposition to be a cutting pattern. And I can go ahead and place that right over top of the carbon. Just like that. Let's take a snapshot and make sure everything still looks good. Just like earlier, if it's a little bit out of focus, I wouldn't worry about it. Just go ahead and cut it. It's better to get it cut than to sit around waiting for it to drift and break off. So that should be pretty good. And we hit play. Make sure your cutting depth is large enough to actually get through the weld. So I didn't change it. It was still a half a micron and it was not enough. All right. Now, if you want to be nice to the next person, it's a good idea. Just take a little thin cut right here on the end of the Omniprobe, and that'll just remove the last little bit of the carbon deposition so that that probe is nice and clean for the next person to use. It's a nice thing to do. Okay, so at this point, the probe is detached from the sample, and we can safely retract it. Let me fix my SEM here a little bit. So what I would recommend you do is move the probe to the left first. Just kind of get it away from the lift out. And then at this point, you can move it directly to park, and it'll back up to park safely. So we're all done with the Omniprobe. Let's go ahead and take out the carbon injector first, and then the Omniprobe. Now, I kind of put the bare minimum of carbon on here. You can kind of see the sample's welded to the grid, but there's still some empty space in there, and it probably could be done more securely. So if you want to add more deposition, the best way to do this is to go rotate this sample 45 degrees from this position, and then you can add more material on this side, and then rotate another 90 degrees from that position, and you can add more material on this side. So just to demonstrate that, let's do a relative 45-degree rotation. And I'm going to turn my FIB beam current back down here to the 80 picoamps. So in this view, you can see here's the sample on the angle relative to the FIB. We can put the gas injector back in. And I will draw a deposition pattern right here. I'll just rotate it a little bit so it's lined up with the side of the sample. And we can put down another couple hundred nanometers of carbon on this side, and then I can rotate 180 or 90 degrees from this point. I can do the same thing on the other side. And that way this will be nice and secure. It shouldn't fall off. Even if you plasma clean the grid, it should be nice and stable. Let's see, you can get rid of the support PC screen, I think. And so what you hopefully will see here is that the deposition, when it's done on this angle, it builds up kind of more uniformly and it fills in that space a little more accurately, which is why I like doing it this way. So what we want to do now is to rotate the sample another 45 degrees, but we can't do that with the gas injector in, so we have to pull out the gas injector. And we're going to rotate a relative 90 from this point. Put that sample right back in the center. We'll double check our FIB orientation. Sample's a little bit on the high side. Some of that is because the stage is not perfectly level, I think, so when you rotate it changes height a little bit. And then we can go ahead and put that carbon injector back in. And we can do another deposition on this side. Just like that. Hit play. And being welded from both sides with carbon, plus the gap in between should have carbon on it too. So this should be very secure, shouldn't fall off at all. All right, so that's all done. Let's take out the gas injector. We can delete our FIB pattern. And now what we're ready to do is to start thinning this sample down. So let's get it lined back up with the horizontal axis of the stage. So let's go back and do our minus 135 rotation. And to thin this sample, we need to tilt to 52 degrees so that the fib is parallel to the edges of this. But we also need to add a little bit of over tilt angle. And that's going to be different for every type of material. For steel samples like this, an extra 2 degrees is usually appropriate, maybe even like 3 degrees. But I think 2 is fine. So I'm going to tilt, instead of going to 52 degrees, I'm going to go to 54 degree tilt. You see we're not quite at the eucentric height of the stage, but that's okay. I'm going to adjust it so we're at the coincident point, not the eucentric. So put the sample in the center of the fib. We'll double check with the SEM, and if we need be, we can adjust the height of the stage. Bring that up to the center, just like that. And looks good. All right, now because we're tilted, we're plus 2 degrees relative to 52, that means we're going to be cutting on this lower side of the sample. When we want to cut on the other side, we're going to go to 50 degrees. So if you're 52 minus 2 degrees, we're cutting on this back side of the sample, and if we're 52 plus 2 degrees, we're cutting on the front side. And if you forget which way it goes, just really exaggerate the differences. So if I, instead of going 2 degrees, like go down to like 30 degrees, and that tells you, once you get to a point where you can see the side poking out of the sample, that tells you which side you should be cutting on. So angles smaller than 52 degrees, we're going to be cutting on this side, and angles bigger than 52 degrees, we're going to be cutting on the bottom side. So make sure you keep that straight, which side of the sample we're cutting on. The first cut we're going to do is going to be a fairly large beam current. We want this to be fairly efficient cutting. So let's go ahead and use that 2.5 nanoamp beam. I think that'll be pretty reasonable for this. And we're going to use that just to cut away this kind of excess material here and just kind of get the edge square and cleaned up. Now, once the beam current has changed, we need to check our focus and astigmatism. There's really nothing to focus on except the sample itself. We can't really focus on the TEM grid over here because it's a considerably taller surface than the sample. So if we focus the fib way up here, we're not going to get really good cut quality because this will be out of focus. So what you want to do is just try to be as quick as possible. Minimize your scanning time as much as you can, and just try to get this top surface of the TEM lift out in focus. So we'll start scanning. We can adjust our focus and adjust our astigmatism. And again, just try to be quick about it. I mean, hopefully you've got plenty of capping material left on there, and that'll help protect the sample. All right, that looks pretty good. So let's go to our pattern. We're going to use a cleaning cross-section pattern for this cut. We're going to draw it on the bottom side of the screen across the whole width of the sample. Make sure you don't cut through your weld. Don't extend your pattern all the way over here. You cut through your weld, your sample's going to fall off, which will be bad. So we'll do something like this. And don't start your pattern way out here. There's nothing out here to cut, so that's just a waste of time. Make your pattern starting right up on the side of the sample. And for this cut, I'm just going to try to remove this sort of white area here. That's the side of the sample. And that will hopefully get everything nice and square. If you remember from earlier, I was using 40 micron depth of cut with the silicon app file. I'm going to go ahead and use that same value. I think it'll work for this application too. So let's go ahead and hit play, and we'll see what happens. So maybe about 2.5 minutes for this cut. What I'm looking for is, as the cleaning cross section progresses over this surface, I want to make sure that I'm completely removing all this material. So if I take a snapshot right now, I shouldn't see anything below where the cut progress line is. So let me let this advance one more time. Okay, so if I take a snapshot, and you see that everything has been removed below the cut line. That's what we want to see. If we're not seeing that, then you either want to go back and repeat the cleaning cross-section pass a second time, or you want to increase your depth of cut if you want to try to do the cut in one pass. And for some samples, it's better to do multiple cuts to remove the side, and other types of samples, I've found it's better to do it all in one cut. Unfortunately, this is, at this point forward, we start to get into more of an art for thinning samples and less of a science. So it's going to be, every sample is a little bit different. It's going to be really dependent on your the focus, the beam conditions you're using, what the sample is, how thick the sample is. You know, for my lift out, how tall this is will affect how it thins. So this is where you really have to just get familiar with your material and get some practice on the FIB, and start to work out a procedure that works for you. So let's take a snapshot and we'll see what's going on. And you see we're starting to have a little bit of the edge left behind the cut. And this is what I was talking about, that you could either go back and increase the depth of cut, or I can just rerun the pattern and try to remove this in a second pass. And that's what I'm going to do. I'm going to do it in 2 cuts. I'm going to let this finish first, and then I'll go back and do that second cut again. All right, so that cut's done. Let's take a snapshot. And actually, it got rid of most of the edge there. I'm pretty happy with that. I don't know if we need to do another cut. Let's take a look with the SEM and see what happened. So we've removed all the redeposition from that side. So we're back to the nice, pretty clean grain structure view. I guess my image is a little on the noisy side. It could probably use some more beam current. But that's nice and clean. So now what we want to do is we want to do that same cut on the back side. Now, if you're not sure what's going to happen over there and you want to see it, then you would keep your stage at 54-degree tilt, and you would do a relative 180-degree rotation. You know, flip this all around, and then you would do the same cut, and that would allow you to look at the other side. I'm pretty sure I know what's going to happen over there, so instead of rotating the stage, I'm just going to go to 50-degree stage tilt, and I'm going to cut the backside blind. And this is considerably faster as long as you trust your setup. So now on my FIB image, I can move my pattern up to the top side of the lift out. Remember to change your scan direction from bottom to top to bottom. And I'm going to do that same exact cut now on this top side. And just like before, I'm just trying to remove this sort of bright white area. That's the taper on the side of the sample. So let's double check our image, and we'll hit play. All right, I'm going to go ahead and stop my pattern because I'm getting a little bit close to my center line of the sample here. So I'm going to stop and let's see what's going on here. So that was the initial cut. Now what we'll do is we're going to drop the beam current on the FIB down, and we're going to do a second cut, which will be hopefully a little bit better quality, and that will reduce this down to electron transparency. Now, if you're trying to figure out how thick or thin the sample is, one technique that I find works really well is to change your accelerating voltage on the SEM and try to find a voltage where the sample starts to become bright. And let's see where that is. I'm going to guess it's probably around 10 or 15 kV right now. But if I go up in beam current, and here, let's go up in, or sorry, if I go up in accelerating voltage, let's go up in beam current a little bit too, just so our image isn't super noisy. At this point, if I image this at 10 kV, I can see that this is still uniform contrast. Let's go a little bit higher voltage. Let's go to 20 kV. There we go. So at 20 kV, you see that everything becomes extremely bright in the lift out, and you kind of lose all your contrast. What that tells me is that this sample is thin enough that a 20 kV electron beam can pass completely through that sample. So you get most of your secondary electron contrast is coming from both sides, which makes it brighter. And a lot of the backscatter contrast is lost because most of that beam is just passing through the sample and it's not scattering, which is why you lose the ability to distinguish like the carbon layer from the platinum. So if you know your material real well, and you know what voltage it becomes transparent, you can use that as a way to measure the thickness, or at least get an idea of the thickness. So somewhere between 10 and 20 kV, this sample is becoming electron transparent. And in theory, I could have that calibrated out to know how thick this is. What I'm going to do is I'm going to use 5 kV as my reference voltage. So for most materials, or at least for silicon or a lot of materials like silicon, they become transparent to 5 kV somewhere around 200, maybe 300 nanometers thick. And for me, that's going to be where I'm going to switch from my 30 kV FIB to my low voltage FIB for my final cleanup cuts. And if none of that makes sense, just bear with me. I think it will in a few minutes here. So we're going to look at this with the 5 kV beam, and we're looking for it to become bright as I thin it. So let's go back to our 54 degree stage tilt. And I've got to check my FIB focus and astigmatism again because I changed to the lower beam current. Okay. And I need to change my scan direction from top to bottom to bottom to top. And now we're going to start thinning this, and we're going to try to get it to around 200 nanometers thick. Now, for a lot of materials, especially things like steel, there can be a lot of residual stress in here, and you can also trigger phase transformations when you thin it with the FIB. Additionally, you create an amorphous layer on this outside with the FIB cut. And all of those things can add to stress, and it can make the sample want to curl up like a little potato chip. To help prevent that, there's a couple different strategies, but the one that I really like is instead of trying to thin this whole thing uniformly, is I try to only thin down as far as necessary and leave the bottom nice and thick. And that'll add some support to this and help keep it from curling up. Now, the way you do that, at least the way I do it, is I've established that a 40 micron depth of cut is cutting off the whole side of the sample. So what I can do is I can drop my depth down substantially. Like say I take it down to, let's just try like 7 microns. And if I run that cut, it will not completely remove the sidewall of the sample. It'll only remove some part of it. And I'll show you what that looks like. So let's set up my pattern just like this, and I'm going to hit play. And let's see what happens. Now I'm going to turn on my iSpy monitor, and let's look maybe like every 2 cleaning cross-section lines, and we'll see what's going on here. Okay, so after that cut's done, let's take a look at what we have here on our SEM. Let's get it in focus, that'll help. So my FIB has only cut down about this far. You can kind of see over here to the right especially, right? There's like a little edge right here. So I've basically made a uniformly thin sample to this point, and then it tapers out and goes back to the full thickness down here. So if I only cared about this region up here, that would be fine. I'd be all set. Now, if I want to push that thin window down a little bit more, what I would do is just keep doing additional cuts. So I leave my pattern exactly where it is. I'm actually going to drop this down a little bit more. Let's do like 4 micron cut. And I'm going to say play, and you see it's starting to bend on me already, right? Hopefully you saw that this little edge is kind of curling around. So I'm going to run this cut again. And this will push the thin window down a little bit more, but we're trying to keep the bottom thick. So starting to bend on me. Now my hope is that when I do my FIB cut on the other side, that this straightens back out again. That would be the perfect situation. It doesn't always, and in that case, this could be a very challenging sample to make. All right, so now you can see that we have this taper down near the bottom, but the top should be, this should be fairly uniform thickness down to about halfway, I think. And we've got a little bit of a bend on the sample. So now we're going to do the same exact thing on the other side. So we're going to go back to 50 degrees. And we're going to change our scan direction to be top to bottom, and we're going to run those same set of cuts this side. Now, this sample's got a little bit of curvature to it now, and what I think I'm going to do is I'm going to rotate my pattern to try to kind of match that curve the best I can. And hopefully what will happen is when I cut away some of this materials, this will straighten back out again. At least that's the idea. But we'll see what happens here. Every sample is unique, and this is where it gets fun. Okay, so let's hit play. And we want to go back and watch this with our SEM. And what we're looking for is this to become bright. And that'll tell me when I need to stop my cleaning cross-section cuts. Let's see if that's straightening back out again. Not really. So maybe there's some residual, like internal residual stress in the microstructure, in which case there's not a whole lot I can do about it. It's going to want to curl up on its own. All right, so we're getting a little bit of electron transparency right over here in the corner. This is in the carbon depth, which kind of makes sense, right? That's the really low atomic number stuff. And also a little bit over here in this corner. So that's where it's turning bright, but the whole middle is probably a little bit fatter in the center there. So let's take a look at our image here with our FIB, and yeah, it's starting to curve even more. So what we got to do to fix this is we probably need to abandon the idea of using the cleaning cross sections, or at least if we do, we've got to use like little short segments and go after little regions of this thing because it's starting to curve on me. We can let's try one more time with this approach, and hopefully it's not going to bend really badly on me. Some materials are just tough to cut like this, and for this training I chose a purposefully difficult one to do. So steel samples with internal stress are not easy. If you're cutting something like a silicon wafer, it won't do this. It'll stay perfectly straight usually until it gets down to like 10 nanometers thick. Yep. So getting a lot of deflection, a lot of bendies. So I'm really hoping when I do the low voltage cleanup that this straightens out a little bit. One of the other things you can do with challenging sample like this is I could have done a smaller lift out. So a 20 micron wide lift out just massively increases the deflection that you're going to get. So if I had done like a 10 micron lift out or a 5 micron wide lift out, it'd be a little bit less prone to curling up on itself. All right, so we're getting electron transparent over here on the side. Probably that's because it's bending into the beam a little bit there. So let's go ahead and stop the pattern. Let's see what's going on here. And it actually looks like it might be straightening out a little bit. I'm kind of happy with that. Let's cut it one more time. Let's see what happens. Sometimes it's hard to tell where this curve is coming from. It might be the bottom kind of flapping out too. It's not always the top that is sticking out. Yeah, see, it's like right here where it's getting cut by the fib. All right, so now we got some pretty serious bending going on. So we better stop with this approach or we're going to wreck this, this part of the sample. So what I propose we do at this point is we could either just like chop that guy off and just say we're done with it. Or we could go to our low voltage beam and we can try to thin this with the lower voltage and see if it straightens out. And that's what I think let's try. So let's drop our fib down to 5 kV. And I'm going to use a little bit higher beam current, 0.36 nanoamps. And when you go to the low voltage, you always want to increase your over tilt angles a little bit more. So we were doing plus and minus 2 degrees. So let's go to plus and minus 4 degrees. So instead of 54, let's go to 56 degrees. And let's try to get the fib in focus. The 5 kV beam is not going to look quite as pretty, but you should be able to see at least where the lift out is. So that looks pretty good. And for this operation, we're just going to put a rectangle pattern on the side of the sample. Nothing special. We can rotate it so that it's kind of aligned with the lift out. Something like this. And we're just going to let that run. And that's just going to kind of gently polish off this whole side. And let's see if we can get this thing to straighten out a little bit. Now, I spy when you're using rectangle patterns will run off a fixed amount of time. So in this case, let's do every like 5 seconds. And we'll just thin it for a few seconds on this side, and then we'll go to the other side and we'll try to thin it evenly. And the hope is that it'll stop curling up on itself. So let's stop this. Let's see if it's getting worse. Not too bad. All right, so let's go back the other way. So 52 minus 4 degrees would be 48. And just to avoid getting into that stuff, actually we're going to go even lower. Let's go down to like 44 degrees. I want to make sure I hit this right from the side and not from on top of that feature right there. At least if I see if I can get it to go a little straighter. So we got our fib right on the side of the sample, and let's hit play and we'll see what happens here. Yikes. So starting to curve up even more. At least it looks like from the SEM image it is. In the FIB image it looks kind of the same though. Now let's just keep cutting and see what happens. We might lose this left side of this sample. I think once I got the fib cut like through this center piece here, it's gonna cause us some trouble. It's gonna want to like bend and flap around in here. Right. So let's go back to the angle I actually wanted to do. 48, not 58. And let's keep cutting here. So we're starting to get a little bit brighter in the carbon layer in here. What I'd really like to see is the top layer of the iron of the steel kind of get like this color, like this brighter contrast. That's going to really tell me that we're kind of down into that sub 200 nanometer range, which is what I'm looking for. Because otherwise, this sample, if put in the TEM, it's going to be miserably thick and not going to produce very nice images. It looks like the low voltage FIB, as it's removing some of this stuff down on the bottom here, it looks like it's straightening out a little bit. So maybe whatever this is, I think there was a grain down there, or like a grain boundary through here. Maybe this was the problem. It was trying to pull the whole sample over into a curve. Let me reposition my FIB cut a little bit, since that sample's starting to straighten out. All right, so I can see here I'm starting to lose my capping layer, which that either tells you you're getting really thin, or it tells you that your tilt angle's not correct. So to kind of prevent hitting the top layer and shortening this too much, we need to increase our over tilt some more. So let's go down to 46. We're doing it, so it's another 2 degrees, and we'll keep trying to thin this some more. So just starting to get some electron transparency right in here. Now I want to remember that I need to cut this evenly. I want to mill on both sides, so I need to leave a little bit of cutting to do on this front side. But it looks like we're starting to get bright. You can see it's kind of getting bright in here. It's definitely bright over here on the right. A little bit more transparent in this area here. Some weird twisting going on here on the end, but I guess that's just going to be how this sample turns out. If your bright areas are showing up way down in the bottom down here, then that tells you that your over tilt angle is too much. So like if your tilt angle's not enough, you're going to selectively cut off the top of your sample. And if your tilt angle's too high, you're going to cut the bottom of the sample. So the idea is to try to find like the perfect value where it mills like right in here. And I'm getting so I can see my thin spots showing up right here and over here. So I think this 46 degrees is too far. So let's back it up a little bit. Let's go back to that 48 and see if I can get this kind of area up here to become thinner. All right, I'm pretty happy with this for now. Let's go and do some cutting on the front side just to kind of keep everything even. So let's go back to our 56-degree tilt. And it looks like the sample might have twisted a little bit because I don't see as much of the side of the sample as I did before. So maybe let's go a little bit higher tilt. Let's go to like 58. Yeah, that looks a little nicer. And let's do some cuts over here. All right, I think that is still, yeah, it's straightening out a little bit, so that's kind of nice. One thing you can do when the samples get this curvy is sometimes you can just put the pattern over top of everything. That'll definitely take out some of your platinum. But there's also no reason why you can't do multiple patterns. So if I put a pattern kind of like here, and then I go and I draw another pattern, kind of angle this one like this. And just make sure they're running in parallel mode, and that'll kind of track that edge a little better. All right, so now we're starting to get our thin spots showing up down here in the bottom. So again, that tells me my over-tilt angle is too extreme. We got to back off a little bit. And we're still thinning a lot down here on the bottom. So let's go back down to like 54. All right. So we're starting to get into a really unstable situation here. Probably 5 kV this is about as far as we can go with 5 kV. And if I want to try to get this any thinner, we should drop my voltage down some more. So let's drop down to 2 kV, and let's see if we can get this a little nicer. There's certainly going to be a real thin region right here where it's, obviously there's a hole there. And then this whole area over here is all going to be real nice, and also up here on the top. But what I was really hoping is get a little bit more uniform across this top, and this is, I guess this sample is just fighting me. It's not going the way I thought it would go. But like I said, deformed stainless steel is a really tricky sample to do. But let's see if we can get it any more improved here. So let's drop down to 2 kV on the FIB. Now the resolution on the 2 kV is not going to be spectacular, but as long as you can see where the sample is, it should be okay. So let's go back up to the other side. Let's go back to that 56 degrees. And 2 kV, we're not really trying to do a lot of thinning here. It's mainly to just remove the damage from the FIB, from the 5 kV beam. So I don't really have a problem with just kind of covering the whole thing with the 2 kV, just kind of like this, and we'll just see what happens. So start scanning. And hopefully this thing doesn't curl up on itself too much. And because I have the FIB scanning over the top of the sample, we're going to be losing our capping layer here a little faster than maybe we otherwise would. But I think that's okay for now. I'm hoping that when the capping layer disappears, that this top edge gets transparent. Because that's the area I was most interested in this sample, was that sort of deformed zone right up there near the top. And we only have a few minutes left, so hopefully I can get this one sorted out before we have to sign off. It's interesting to me. This sample is going back straight again when I'm cutting it with 2 kV, which makes me think that the bending on this sample might be related to some kind of FIB-induced stress. So when you do the low voltage cut, it removes that, and then it goes back straight. Because it's almost back to as straight as it was when we started. Now, especially with the 2 kV beam, if I've got it pretty well thinned over here on the left side, if I need this right side to kind of catch up, what I'll do here is shift my pattern over so that I'm only milling kind of that left part of the sample. And I wouldn't do this probably at the 30 kV condition, but at the 2 kV, it's not going to cause too much trouble, and try to get this area a little thinner compared to over on the left side. you can cause some redeposition type contamination to show up over here because it's not the fib's only hitting this right side. So when you're done with this step, you always want to do a cleanup pass over the whole thing, just to make sure there's no contaminants over here. So we're still milling down at the bottom more than the top. So let's bring our tilt angle down a little bit more. Let's come back down to like 54. All right, let's cut on the other side a little bit. So let's go over back to that 48 degrees. And I think we're going to have to call it a day on this one. If it was a real sample, I'd probably keep working on this, trying to get this top to thin up, but I just don't think I have time left on today's session to keep doing that. So let's see what happens when we cut it on the backside for a few seconds. Because I just think my gut feeling is it's too thick for any kind of reasonable TEM right now. It is starting to get brighter though. This area in here is starting to lighten up. So maybe there's some hope here. Once the sample gets really thin, if you start to lose any contrast and you want to get it back, what we want to do is just drop your voltage down on your SEM. So if I take my SEM down to say 3 kV, that's going to show me where the really thin spots are. So anything that's, especially in iron, if it's electron transparent at 3 kV, this is going to be really thin. But I can tell now that, you know, up here across the top is not as thin as down here, and probably we should keep working at this sample. All right, let's do one more cut here for another minute or so, and then we're going to call it a day. All right, I think that's as good as we're going to get. We're almost out of our deposition, our capping material over here. We've lost it way a long time ago. We lost it over here on the left side. So maybe not the most fantastic sample I've ever made, but I think it would probably work for the TEM. It's kind of tricky at this point to figure out how thick this actually is. If you're doing a bunch of samples, what you can do is do like a throwaway sample, thin it like this, and then you can cut through it with the FIB and then measure it directly with SEM. That might be something kind of fun to do. I don't want to put this in the TEM. Yeah, why not? Let's just do it. And let's see how thick it is here. So first of all, I want to see what voltage it becomes electron transparent in this region. So let's turn up the voltage. Let's go to 4 kV. Let's go to 6 kV. Let's see here. All right, so at 6 kV, right here, definitely electron transparent at 6 kV, right in that spot. That was kind of the area I was aiming for. Let's turn it down a little bit. Let's go to 5500. And still a little transparency there, but not much. So let's call it that. So we're at imaging at 5500 kV, and it's just starting to turn bright right in here. So what I'm going to do, and this is going to probably seem crazy, is I'm going to coat this with some platinum, and I'm going to chop that off with the FIB, and we'll see how thick it is right there. Let's see how we did. My guess is it's probably around 150 to 200 nanometers. So let's put in the gas injector, and I'm going to do a platinum pattern. Just like that. Let's hit go. Obvious. I should, hopefully it's obvious, but don't do this on a sample that you care about. This is going to destroy this sample. Let me drop down. I need a little more beam current for doing this. 2 kV. All right, so now what we want to do is, so I want to spin this around so the FIB can see where that platinum is. And then I'm going to cut a little hole through the sample right there, and then we should be able to see it with the SEM, how thick it actually was. No, I didn't get much platinum there, huh? All right, relative. All right. So if you have a thin sample like this and you take a picture of it with 30 kV, you're going to wreck it instantly. So you can kind of see that even every picture I take, this sample's bending. So 30 kV is going to destroy a thin sample if you're not careful. Just to show you how fast this goes, if I start imaging this thing at 30 kV, you can see it's just all like curling up and falling apart. All right, so what I want to do is I want to make a little cut right here. So it's sort of like a cross section. I'm using that platinum as a bare hard mask to cut through. All right, so now what we want to do is we're going to rotate our stage 90 degrees. And we're going to tilt. Let's go to like 45 degrees. And we're going to need the high resolution lens to see this. All right, so where's my cut? All right, so you can kind of see, I think this this stuff here is the platinum deposition on both sides. It builds up on both sides because the electron beam can go through it. So the sample is, well, apart from being really blurry and out of focus, this is the sample from here to here. So maybe I can try to get this a little better focused. There, okay, there we go. So, actually, no, I made a mistake. This is the sample right here. This is the platinum. So there's the original top of the sample. Yeah, I'm almost done. And so if we measure that up near the top of the carbon, that was where I said my good area was. Yeah, we're like 60 nanometers. That's actually not too bad. And further down where it got a little chunky, it's like 116. So not, I guess not as bad as I thought it was. Probably would have been an okay sample after all for the TEM, but it's definitely one of the harder things to do is to measure the sample thickness without doing something drastic like this, like cutting your sample in half. Yeah, so for the stainless steel, I guess when it becomes bright at a 5.5 kV beam, then we know it's somewhere in the order of like 80 nanometers, 70 nanometers thick, something like that. So I guess the next time I do this sample, I'll have an idea of how thin it actually is. But that's kind of how you do this. the other way you could do it is measure it in the TEM with eels or something and get an idea of the thickness variation that way. All right, so that's the basics of making a TEM sample and cutting it in half when you're done. And let's go ahead and, if you guys have any questions while I'm shutting down the tool, please ask, but I'm only going to stay on for another couple minutes while I'm venting the chamber.
I got a quick question.
Yeah.
So other than Helios, is there any other instrument I can do the FIB SEM with the EDS?
Yeah, every single one of our SEMs in the lab has EDS. So the Helios has the 3D software for doing 3D EDS, but any of the FIBs, so the Nova, the Helios 650, or the Helios Plasma FIB, they all have EDS detectors. So you can do cross sections and then do EDS maps on those tools. But if you want to do 3D tomography with EDS, the Helios 650 is the only one with that software.
Okay.
But
the reason is because it's already fully booked, so I'm just thinking, is there an alternative instrument I can do the FIB SEM with EDS?
Like I said, if you only want to do like static EDS maps after you cross section, then you can do it on the Nova or the Plasma FIB as well. The other thing you can do is you can do a FIB cut on a sample, and you can take the sample out and go to another microscope and do the SEM map on the cross section after it's cut. There's no reason it has to be done on the same tool.
Right. Okay.
But yeah, I know the Helios is always busy. It's just everyone likes to use this tool, so.
Okay. Thanks.
Yep. Are there any other questions? Let me just double check, make sure there aren't any on the YouTube chat. I don't think there are, but yeah, doesn't look like there's any questions on the YouTube chat. So I guess with that, I'm going to sign off, and I look forward to seeing all of you in the lab and ask me questions if you have them. All right, have a good evening, everyone.
Cool. Thank you so much.